Hey there, cosmic explorers. Before we dive into one of the most mind-blowing journeys through space and time, I need to ask you something. Have you ever looked up at the night sky and wondered what's hiding in that bright band of stars we call the Milky Way? Well, I'm about to blow your mind. Right now, as you're watching this video, there's something lurking at the very center of our galaxy. Something so massive, so powerful, and so mysterious that it makes everything else in the cosmos look like child's play. We're talking about a monster that weighs as much as 4 million suns, crammed into a space smaller than our solar system. And here's the kicker, you can't see it. Not with your eyes, not with a regular telescope, not even with the most powerful instruments humans have ever built. Until recently. This is the story of the supermassive black hole at the center of the Milky Way. And trust me, by the time we're done here, you'll never look at the night sky the same way again. If you're the kind of person who loves having your mind expanded by the wonders of the universe, do me a favor right now. Hit that subscribe button and ring the notification bell. I promise you, this channel is going to take you on journeys that most people never even dream about. And if you find this video as fascinating as I think you will, share it with someone who needs a little cosmic wonder in their life. Science is always better when we explore it together. Now, let's begin our adventure into the dark heart of the Milky Way. Chapter 1. The Hidden Center. Picture yourself standing outside on a clear, dark night, far away from the lights of any city. You look up, and there it is, the Milky Way, stretching across the sky like a river of light. It's beautiful, isn't it? That soft, glowing band has inspired poets, artists, and dreamers for thousands of years. But here's something that might surprise you. For most of human history, we had absolutely no idea what we were looking at. Ancient people came up with all sorts of explanations. Some thought it was milk spilled by the gods. Others believed it was a pathway for souls traveling to the afterlife. The ancient Greeks called it Galaxias Kyklos, the Milky Circle, which is where we get the word galaxy from. It wasn't until we started building telescopes and studying the sky with scientific methods that we began to understand the truth. That band of light isn't some mystical substance, it's stars. Billions and billions of stars, packed so closely together from our point of view that they blur into a continuous glow. But even after astronomers figured that out, there was still a huge mystery at the center of it all. When they turned their telescopes toward the thickest, brightest part of the Milky Way, toward the constellation Sagittarius, they ran into a problem. They couldn't see through it. Let me explain why this was such a big deal. Imagine you're trying to look through a fog. Close things are visible, but the further away something is, the hazier it gets until eventually you can't see anything at all. That's essentially what was happening when astronomers tried to peer into the heart of our galaxy. The culprit, dust, not the kind of dust you find under your bed, but cosmic dust, tiny particles of carbon, ice, and rock floating in the vast spaces between stars. These particles are incredibly small, but there are so many of them spread across such enormous distances that they effectively block visible light from passing through. And nowhere in our entire galaxy is there more of this dust than in the direction of the galactic center. It's like someone hung a curtain right in front of the most interesting part of the show. This region is called the Galactic Bulge, and it's one of the most crowded neighborhoods in the entire Milky Way. Picture a huge central swelling, like the yolk of a fried egg, packed with hundreds of billions of stars. From Earth, this bulge lies directly in the path of anyone trying to see what's at the very center of the galaxy. For centuries, astronomers were essentially blind to the heart of our cosmic home. They could map the outer arms of the Milky Way, track the movements of nearby stars, and chart the positions of planets. But the center, that remained one of the great mysteries of the universe. Some early scientists thought the sun must be near the center of the galaxy. After all, when they looked around, they saw stars in every direction. It seemed logical that we must be somewhere in the middle of things. But they were fooling themselves. The only reason stars appeared evenly distributed was because they couldn't see past the dust in the direction of the true center. It was like standing in a foggy room and assuming you're in the middle, just because you can't see the walls. In the 18th and 19th centuries, brilliant astronomers tried to map the shape of our galaxy by counting stars in different directions. The idea was clever. If you count more stars in one direction than another, that tells you something about the galaxy's structure. But these early map makers didn't know about interstellar dust. When their counts came up uneven, they assumed it was because the galaxy itself was shaped unevenly. In reality, the dust was hiding vast regions from their view. It wasn't until the 20th century that everything began to change. Scientists realized that if they wanted to see through the cosmic fog, they needed to stop relying on visible light. They needed to look at the universe in completely different ways, using forms of light that could slip right through the dust without being blocked. This is where things start to get really exciting, because once we learned to see with new kinds of eyes, the hidden center of our galaxy finally began to reveal its secrets. And what we found there was beyond anything anyone had imagined. Chapter 2: The Signal That Changed Everything. Our story takes a surprising turn in the early 1930s. In a place you might not expect, a telephone company laboratory in New Jersey. A young engineer was working on a very practical problem. His name isn't important for our story, but what he discovered absolutely is. His job was to figure out why long-distance radio communications were being disrupted by strange static. At the time, radio was becoming increasingly important. Ships at sea needed to communicate. Stations were broadcasting news and entertainment, and countries were relying on clear signals for all sorts of purposes. But there was this annoying background noise that nobody could explain. To track down the source of the interference, this engineer built a peculiar-looking machine. It was a large rotating antenna mounted on wheels, which some people jokingly called a merry-go-round because you could spin it around to face different parts of the sky. The antenna was designed to pick up radio waves, the same kind of waves that carry signals to your car radio, but at slightly different frequencies. For months, he collected data, carefully recording where the mysterious static was coming from. He found that some of it originated from nearby thunderstorms. Some came from distant lightning strikes. But there was one source of noise that behaved very differently from all the others. This particular signal came and went in a regular pattern, roughly once every 24 hours. At first, he thought it must be related to the sun. That would make sense, right? The sun is a massive ball of burning gas, and it produces all kinds of radiation. Maybe it was sending out radio waves too. But as he tracked the signal more carefully, he noticed something odd. The timing didn't quite match up with the sun's position. The signal arrived about 4 minutes earlier each day. That might not sound like much, but it was a crucial clue. See, here's the thing about time and astronomy. The Earth rotates once every 24 hours relative to the sun, but relative to the distant stars, it rotates about 4 minutes faster. This is because the Earth is also moving around the sun, so our planet has to turn just a little bit extra each day to face the sun again. What this meant was that the mysterious radio signal wasn't coming from the sun at all. It was coming from a fixed point in the sky, a point among the stars. And when he traced exactly where that point was, it led directly toward the center of the Milky Way. This was absolutely revolutionary. For the first time in human history, someone had detected radio waves coming from beyond our solar system. It was a complete accident, a side effect of troubleshooting communication problems, but it opened an entirely new window on the universe. At first, the scientific community didn't pay much attention. Astronomers were used to working with light they could see through telescopes, and radio waves seemed like a strange curiosity at best. The original discovery was published and then largely forgotten as the world moved on to other concerns. But a seed had been planted. A few years later, another engineer became fascinated by this discovery. He decided to build his own radio telescope right in his backyard. Using his own money and his own time, he constructed a large dish-shaped antenna, about 9 meters across, and started scanning the sky for radio signals. What he found confirmed everything. There was indeed a powerful source of radio waves coming from the direction of Sagittarius, right where the galactic center should be. His homemade telescope produced the first radio maps of the sky, showing that objects completely invisible to optical telescopes could shine brightly in radio waves. Throughout the 1940s and 50s, more scientists joined this new field of radio astronomy. They built bigger and more sensitive antennas, developing techniques to pinpoint exactly where these cosmic radio signals were coming from. And one spot kept showing up as especially interesting: a compact, powerful source of radio waves sitting right at the heart of the Milky Way. This source was steady, strong, and incredibly small compared to the vastness around it. It didn't flicker randomly like many radio sources do. It was concentrated in one tiny region of space, which suggested it was coming from something extremely dense and extremely powerful. But what could it be? For decades, nobody knew for certain. The signal was there, clear as day to radio telescopes, but it didn't match the characteristics of any known astronomical object. It wasn't a typical cloud of gas. It didn't look like the remnant of an exploded star. Something very strange was lurking at the center of our galaxy. To find out what it was, astronomers would need to track something even more revealing than radio waves. They would need to watch how stars move in that mysterious central region. And that would require patience, precision, and an entirely new way of looking at the invisible. Chapter 3: Eyes That See Through Darkness. If visible light can't penetrate the dust clouds blocking our view of the galactic center, and radio waves can only tell us so much, what's the solution? The answer came from a type of light that sits right between visible and radio on the electromagnetic spectrum: infrared radiation. You've probably heard of infrared before. Night vision goggles use it. Thermal cameras detect it. Your TV remote control sends signals with it. Infrared is essentially heat radiation. Everything that has any warmth at all emits infrared light. The beautiful thing about infrared is that it can pass through dust much more easily than visible light can. Those tiny particles that scatter and absorb the light our eyes can see are almost transparent to infrared wavelengths. This means that if we could build telescopes that detect infrared instead of visible light, we could peer through the cosmic fog and see what's on the other side. The problem is that infrared astronomy is really hard to do from the ground. Earth's atmosphere absorbs a lot of infrared radiation before it ever reaches our telescopes. Plus, everything on Earth emits infrared: the ground, the air, even the telescope itself. It's like trying to see faint stars while someone is shining a flashlight in your face. Scientists came up with clever solutions. They put infrared telescopes on mountaintops, where the air is thin and dry. Places like the summit of a certain volcanic mountain in Hawaii or the high deserts of Chile offer some of the best conditions on Earth for infrared observations. At these elevations, there's less atmosphere to absorb the incoming signals, and the dry air contains less water vapor, which is one of the worst infrared blockers. Even better than mountaintops, though, is getting above the atmosphere entirely. Starting in the 1980s, space agencies began launching infrared telescopes into orbit. Free from atmospheric interference, these instruments could see the infrared universe with unprecedented clarity. The results were stunning. Regions of space that looked completely dark and visible light suddenly lit up with activity. The heart of the Milky Way, which had been hidden behind that impenetrable wall of dust for so long, began to reveal itself. And what astronomers saw was not what they expected. The galactic center wasn't empty or quiet. It was teeming with stars, millions of them, packed into a relatively small region of space. These stars were orbiting something, moving in complex paths around a central point, and they were moving fast, really fast. This is where the story gets truly amazing. By tracking the positions of individual stars over many years, astronomers could work out their orbits. It's the same basic principle that allowed ancient scientists to figure out that Earth orbits the Sun. If you watch something long enough and carefully enough, you can see the pattern in its movement. But watching stars at the center of the galaxy is incredibly challenging. They're 26,000 light-years away from us. At that distance, even with our best telescopes, the stars appear as tiny dots of light that shift position by incredibly small amounts each year. We're talking about movements so small that you'd need to measure them in fractions of a millionth of a degree. To make matters worse, Earth's atmosphere creates constant problems. The air above us is never perfectly still. there are currents and temperature variations that make starlight shimmer and blur. This is why stars twinkle when you look at them with your naked eye. It's pretty, but for astronomers trying to make precise measurements, it's a nightmare. The solution came from a brilliant technology called adaptive optics. Here's how it works. Instead of trying to design a telescope that can somehow see through the atmospheric distortion, you build a telescope with a flexible mirror that can change shape in real time. To cancel out the distortion, the telescope constantly monitors a reference point in the sky, either a bright star or an artificial star created by shining a powerful laser into the upper atmosphere. By analyzing how that reference point appears to wobble and shift, computers can calculate exactly how the atmosphere is bending the light at any given moment. Then, hundreds of times per second, tiny motors push and pull on different parts of the mirror to counteract those distortions. The result is that blurry, shimmering images suddenly snap into focus. Stars that were fuzzy blobs become sharp points of light. And for the first time, astronomers could track the precise movements of stars in the crowded chaos of the galactic center. To research teams working independently on opposite sides of the world spent years making these painstaking observations. One team worked from observatories in Chile, the other from Hawaii. Both groups used adaptive optics to pierce the dust and follow the paths of stars. As they whipped around the galactic center, what they discovered would change our understanding of the universe forever. Chapter 4: The Dance of Stars. Let me paint you a picture of what these astronomers were seeing. Imagine looking at the very heart of our galaxy, zoomed in as far as our technology allows. You see a cluster of stars, some bright, some dim, all packed into a region of space that, while enormous by human standards, is tiny compared to the galaxy as a whole. Now imagine watching these stars year after year after year. At first, nothing seems to change. The stars are so far away that even their rapid motion takes time to become apparent. But after a few years, you start to notice something. The stars aren't staying still. They're moving. Not just drifting randomly, either. They're following precise paths, like planets orbiting a sun. Some of these paths are nearly circular. Others are elongated ellipses that swing the stars close to the center and then fling them far out before bringing them back again. And the speeds involved are absolutely mind-boggling. Some of these stars are traveling at over 5,000 kilometers per second. To put that in perspective, at that speed you could travel from Earth to the Moon in about a minute. These stars are screaming through space at a significant fraction of the speed of light. One star in particular became incredibly important for our story. Astronomers gave it a simple designation, S2. This star follows a highly elongated orbit that brings it extremely close to whatever is sitting at the center of the galaxy, then swings it back out again. The complete journey takes only about 16 years. 16 years might sound like a long time, but for a star orbiting the center of a galaxy, it's remarkably fast. Our own sun takes about 230 million years to complete one orbit around the Milky Way. S2 does its orbit almost 15 million times faster relative to how close it is to the center. By tracking S2's motion with exquisite precision, astronomers could apply the same laws of physics that govern the motion of planets. In our solar system, when a smaller object orbits a larger one, the shape of its orbit and its speed at different points along that orbit tell you exactly how much mass is doing the pulling. The calculations were done and checked and double-checked. Both research teams, working completely independently with different telescopes and different methods, came to the same staggering conclusion. Whatever S2 was orbiting had a mass of about 4 million times that of our sun. Let that sink in for a moment. 4 million suns, all crammed into a region of space smaller than our solar system, probably smaller than the distance from the sun to the outer planets. But here's the really weird part. This incredibly massive thing was essentially invisible. It wasn't shining like a star. It wasn't glowing like a cloud of hot gas. Invisible light, infrared, and most other wavelengths, there was almost nothing there. Just a tiny radio source that had been puzzling astronomers for decades. There was only one type of object known to physics that could have that much mass. In that small a space, while remaining almost completely dark. A black hole. And not just any black hole, a supermassive black hole, the largest type known to exist. The kind of monster that sits at the center of galaxies and shapes everything around it. Through the sheer power of its gravity, the evidence was overwhelming. Every star tracked near the galactic center pointed toward the same central object. The orbits behaved exactly as Einstein's general theory of relativity predicted. They should near an extremely massive compact object. There was simply no other explanation that fit the data. After decades of searching, humanity had finally found definitive proof of a supermassive black hole at the heart of our home galaxy. And it had been there all along, hidden behind clouds of dust, pulling on stars with its invisible hands. Chapter 5. What exactly is a black hole? Okay, let's pause for a moment and make sure we're all on the same page about what a black hole actually is, because the term gets thrown around a lot in science fiction and popular culture, and there are a lot of misconceptions out there. A black hole is not a hole in space, despite what the name might suggest. It's not a portal to another dimension, probably. It's not a cosmic vacuum cleaner that sucks in everything around it. A black hole is, at its core, simply a region of space where gravity is so incredibly strong that nothing, not matter, not light, not even information, can escape once it crosses a certain boundary. Let's break this down with an analogy. Imagine you're standing on the surface of Earth and you throw a ball straight up into the air. The ball rises for a while, slows down because of Earth's gravity, and eventually falls back down. If you throw the ball harder, it goes higher before falling. Throw it really hard, about 11 kilometers per second, to be precise, and it will escape Earth's gravity entirely and fly off into space. That speed, the minimum speed needed to escape a gravitational pull, is called the escape velocity. Every object with mass has an escape velocity that depends on how massive it is and how close you are to its center. Now here's where things get interesting. What if you could squeeze Earth down to a smaller and smaller size, while keeping all its mass the same? The escape velocity at its surface would get higher and higher as you got closer to all that mass. At some point, if you squeezed Earth small enough, to about the size of a marble, actually, the escape velocity at its surface would exceed the speed of light. And since nothing can travel faster than light, one of the fundamental rules of the universe, as we understand it, nothing could escape. Not even light itself. At that point, you'd have a black hole. The boundary where the escape velocity equals the speed of light is called the event horizon. It's not a physical surface. There's nothing solid there. It's simply the point of no return. Cross that line and you're committed. No amount of rocket power, no tricks, no escape. You're going into the black hole. This is why black holes are black. They don't emit light, because any light that would come from them can't get past the event horizon. They're like perfectly dark spheres in space, or rather, perfectly dark spherical regions. Since there's no actual surface to touch, the size of a black hole's event horizon depends entirely on its mass. More massive black holes have larger event horizons. The relationship is pretty simple. Double the mass, double the radius of the event horizon. For the black hole at the center of our galaxy, with its vermilion solar masses, the event horizon has a radius of roughly 12 million kilometers. That sounds huge, but remember, the Sun itself has a radius of about 700,000 kilometers. So this black hole's event horizon is only about 17 times larger than the Sun, while containing 4 million times as much mass. Everything inside that 12 million kilometer sphere is cut off from the rest of the universe. We don't know what happens inside. The known laws of physics break down as you approach the center, where all the mass is theoretically compressed into an infinitely small, infinitely dense point called a singularity. Whether the singularity is actually a point, or whether something more complex happens there, is one of the great unsolved mysteries of physics. We might never know for certain, because no information can ever escape to tell us. What we can study is everything that happens outside the event horizon. And that's where things get really interesting. Chapter 6, the name that stuck. Before we go further, let's talk about why this particular black hole has such an unusual name. You've probably heard it referred to as Sagittarius A star, written with an asterisk at the end. But where did that name come from? As we discussed earlier, when astronomers first detected radio waves from the center of the galaxy, they needed a way to catalog what they were finding. The radio source was located in the direction of the constellation Sagittarius, so they named the whole complex of radio signals in that region Sagittarius A, the first major radio source found in that part of the sky. But as technology improved, astronomers realized that Sagittarius A wasn't just one object. It was a cluster of different radio sources, all located near the galactic center. The brightest, most compact source at the very heart of this cluster needed its own designation to distinguish it from the surrounding emission. To astronomers studying this region in the early 1970s needed a way to indicate that this particular point source was something special, more intense, more concentrated, and more interesting than the diffuse radio glow around it. They borrowed a notation from atomic physics, where an asterisk is sometimes used to indicate an excited state, a version of an atom, with more energy than usual. So they called this intense, compact source Sagittarius A star, with the asterisk indicating its unique, energetic nature. The name stuck, even as we came to understand that this was actually a supermassive black hole. The designation remained. It's a bit ironic, when you think about it, calling something a star when it's actually the opposite of a star. In almost every way, stars shine with their own light. Black holes absorb light. Stars push outward with radiation pressure. Black holes pull inward with gravity. But that's how astronomical naming often works. Names get attached for historical reasons, and then stick around long after our understanding has changed. We still call Mars's moons Phobos and Deimos even though they're tiny potato-shaped rocks, not the fearsome gods of Greek mythology. In the case of our galactic black hole, the name serves as a reminder of the long journey of discovery that led us to understand what it really is. Every time someone says Sagittarius A star, they're unconsciously echoing decades of scientific progress. From the first accidental detection of radio waves to the sophisticated observations that proved a monster lurks at the center of our cosmic home. Chapter 7, not all black holes are created equal. Now that we understand what a black hole is and how we found the one at our galaxy's center, let's zoom out for a moment and look at the bigger picture. Because Sagittarius A star isn't the only black hole in the universe, not by a long shot. Black holes come in different sizes, and the way they form can vary dramatically. Understanding these different types helps us appreciate just how unusual and significant our galactic black hole really is. The most common type of black hole is called a stellar mass black hole. These form when massive stars die. Throughout their lives, stars are engaged in a constant battle between two forces, gravity trying to crush them inward, and the outward pressure from nuclear fusion reactions in their cores. As long as fusion is happening, the star remains stable. But eventually, every star runs out of fuel. When that happens to a really massive star, one at least 20 times heavier than our Sun, the results are catastrophic. The core collapses under its own gravity in a matter of seconds, and the outer layers explode outward in a supernova. If the collapsing core is massive enough, nothing can stop the implosion, and a black hole is born. These stellar mass black holes are relatively small, typically between about 5 and 50 times the mass of the Sun. That might sound like a lot, but compared to Sagittarius A star, they're tiny. Their event horizons might only be a few kilometers across, small enough to fit inside a city. At the other end of the scale are the supermassive black holes, like the one at our galactic center. These monsters range from millions to billions of times the mass of the Sun. They're so big that their event horizons can be larger than our entire solar system. Here's the puzzle: supermassive black holes couldn't have formed the same way stellar mass black holes do. A single star, no matter how massive, could never produce something 4,000,000 times heavier than the Sun. There simply wasn't enough material to begin with. So how did Sagittarius A star get so big? This is one of the great mysteries in modern astrophysics, and we don't have a complete answer yet. But there are several theories. One idea is that supermassive black holes started as smaller seed black holes that formed very early in the universe's history. These seeds might have been the remnants of the very first generation of stars, which were probably much larger than any stars that exist today. Over billions of years, these seeds could have grown by consuming gas, dust, and occasional stars that wandered too close. Another possibility is that some supermassive black holes formed directly, without going through a stellar stage at all. In the very early universe, enormous clouds of primordial gas might have collapsed under their own gravity so quickly that they skipped the whole star-forming process and went straight to becoming black holes. These direct collapse black holes could have started out already weighing tens of thousands of solar masses. There's also the merger scenario. We know that galaxies collide and merge over cosmic time. In fact, our own Milky Way is on a collision course with the Andromeda Galaxy, but don't worry. We have billions of years before that happens. When galaxies merge, their central black holes eventually find each other and combine into a single, larger black hole. Over many such mergers across billions of years, a modest-sized black hole could grow into a true monster. The truth is probably a combination of all these processes. Sagittarius, a star, likely started as something smaller and has been growing throughout the entire history of the Milky Way, slowly consuming gas and dust, occasionally swallowing a star, and possibly merging with other black holes from smaller galaxies that our galaxy has absorbed. There's another category worth mentioning: intermediate mass black holes. These would fall between stellar mass and supermassive, ranging from hundreds to tens of thousands of solar masses. They're theoretically possible and might form in dense star clusters, where multiple stellar mass black holes merge together, but they've been incredibly hard to find. We have a few candidates, but none as definitively confirmed as either stellar mass black holes or supermassive ones. If intermediate mass black holes exist in large numbers, they might represent a stepping stone in the growth of supermassive black holes, a missing link in the cosmic size ladder. Finding more of them would help us understand how monsters like Sagittarius, a star, came to be. Finally, there are hypothetical types of black holes that remain purely theoretical for now. Primordial black holes might have formed in the extreme conditions of the Big Bang itself, from density fluctuations in the very early universe. They could be any size, from microscopic to massive, depending on when and how they formed. If they exist, they might be scattered throughout the universe, possibly even passing through our solar system from time to time without us noticing. And at the very extreme end of the scale, there might be ultramassive black holes, objects containing more than 10 billion times the mass of the Sun. A few candidates have been identified in the centers of particularly gigantic galaxies. If they're real, they push the limits of how fast we think black holes can grow. In this grand cosmic menagerie, Sagittarius, a star, occupies a middle ground. At 4 million solar masses, it's definitely supermassive, but it's actually on the smaller side for black holes of this type. Some galaxies harbor black holes hundreds or thousands of times more massive than ours. But what Sagittarius, a star, lacks in size, it makes up for in accessibility. It's the closest supermassive black hole to Earth, which makes it the best laboratory we have for studying these cosmic titans up close. Chapter 8: The Giants of the Cosmos. Let's put Sagittarius, a star, in perspective by comparing it to some of the other supermassive black holes we've discovered throughout the universe. Trust me, this comparison will really drive home just how wild the scale of these objects can get. If Sagittarius, a star, were somehow transported to the center of our solar system, replacing the Sun, its event horizon would extend far past the orbits of the inner planets. Mercury, Venus, Earth, Mars, all would find themselves inside the black hole's point of no return. We wouldn't even have time to notice before everything went dark forever. That sounds catastrophic, and it is. But in the hierarchy of cosmic black holes, Sagittarius, a star, isn't even close to being the biggest kid on the block. Take the black hole at the center of a massive elliptical galaxy, about 55 million light-years away. This monster weighs in at approximately 6.5 billion solar masses, over 1,000 times more massive than our galactic black hole. Its event horizon is so enormous that our entire solar system, including the distant outer reaches where comets drift in the cold, would fit comfortably inside with room to spare. This black hole became famous when it became the first to ever be directly imaged. But even it isn't the largest. There's another black hole at the center of a galaxy cluster over 700 million light-years distant that tips the scales at around 20 billion solar masses. If you lined up Sagittarius' star end to end, you'd need 5,000 of them to equal this single behemoth. And then there's something even more extreme, a class of objects called quasars, which are essentially supermassive black holes that are actively gorging themselves on enormous amounts of matter. The brightest quasars harbor black holes estimated at 40 billion solar masses or more. Let that number sink in. 40 billion suns. You could take 10,000 copies of Sagittarius' star and combine them all, and you still wouldn't reach the mass of these cosmic titans. The event horizon of a 40 billion solar mass black hole would be so vast that light would take about a week to travel across it. For comparison, light crosses Sagittarius' star's event horizon in about 24 seconds. We're talking about a difference in scale that's almost impossible to visualize. So why is Sagittarius' star so much smaller than these cosmic monsters? Part of the answer is the environment. These ultramassive black holes typically sit at the centers of giant elliptical galaxies, or in the hearts of galaxy clusters, where there's an enormous amount of gas and matter available to feed their growth. They've likely gone through multiple periods of intense feeding, plus numerous mergers with other massive black holes as galaxies collided and combined over billions of years. The Milky Way, by contrast, is a relatively calm spiral galaxy. We're not at the center of a massive cluster. We haven't undergone a truly major merger in a long time. The conditions here simply haven't been conducive to growing a supergiant black hole. But perhaps more importantly, Sagittarius' star is currently in a very quiet phase of its existence. It's barely feeding at all compared to its more voracious cousins. Those distant quasars, with their billions of solar masses, are surrounded by blazing disks of superheated material spiraling inward. As matter falls toward these black holes, it gets compressed, heated to millions of degrees, and releases tremendous amounts of energy before disappearing past the event horizon. Some quasars are so bright that they outshine their entire host galaxies, trillions of stars worth of light, all coming from a region smaller than our solar system. Sagittarius' star, on the other hand, is essentially napping. There's relatively little gas near it, and what does drift close doesn't fall inefficiently. The black hole at the heart of our galaxy produces only a feeble glow in radio waves and occasional flickers in X-rays, nothing like the cosmic beacons powered by its larger, hungrier relatives. This quietness is actually a blessing for life in the Milky Way. If Sagittarius' star were actively feeding like a quasar, the intense radiation pouring out from its surroundings could potentially affect planets throughout the galaxy. High-energy particles and electromagnetic radiation could strip atmospheres, trigger chemical changes, or even sterilize worlds. The fact that our galactic black hole is essentially dormant means the Milky Way is a relatively calm place for planets and, possibly, life to exist. But the quiet won't last forever. Chapter 9, The Quiet Giant. One of the most puzzling things about Sagittarius' star is just how subdued it is. Here you have an object with 4 million times the mass of the Sun, surrounded by millions of stars and clouds of gas, and yet it barely emits any radiation at all. Compared to the blazing black holes at the centers of active galaxies, ours is practically invisible. Why is it so quiet? The answer lies in the balance between the black hole and its surroundings. A black hole only shines when it has something to eat. Matter falling toward the event horizon gets heated to extreme temperatures, and that hot material radiates energy across the electromagnetic spectrum, radio waves, infrared, visible light, X-rays, even gamma rays. The more matter that falls in, the brighter the emission. But Sagittarius, a star, isn't getting much of a meal. The region around it is surprisingly sparse. While there are plenty of stars in the galactic center, they're mostly in stable orbits that keep them safely away from the black hole. The gas and dust clouds that do drift nearby tend to be scattered, and much of this material never makes it all the way to the event horizon. Here's what seems to be happening when gas approaches Sagittarius, a star. It doesn't fall straight in. Instead, it goes into orbit, forming a thin, sparse structure called an accretion flow. But this flow is so tenuous, so spread out, that it can't build up enough density to glow brightly. Much of the gas actually gets pushed back out by magnetic fields and turbulence before it ever reaches the point of no return. Scientists sometimes describe this as a radiatively inefficient accretion flow. In simpler terms, the stuff falling toward the black hole isn't radiating much energy because it's too thin and disorganized to heat up effectively. Imagine trying to build a campfire, but instead of stacking the logs tightly together, you scatter them loosely in a wide circle. Some heat would still be there, but you'd never get the bright, roaring flame you're looking for. That's similar to what's happening around Sagittarius, a star. This quiet state appears to be temporary, at least on cosmic time scales. There's evidence that our galactic black hole was much more active in the relatively recent past. Recent meaning within the last few hundred years, which is practically yesterday in astronomical terms. The evidence comes from something called light echoes. When a bright event happens near the galactic center, the light doesn't just travel straight to us. Some of it bounces off nearby clouds of gas and dust before continuing on its journey. Because this reflected light takes a longer path, it arrives at Earth later than the direct light did. By studying the brightness and characteristics of certain gas clouds near the galactic center, astronomers have found signatures that suggest Sagittarius, a star, was much more luminous. A few hundred years ago, possibly hundreds of thousands of times brighter than it is now. Something triggered a feeding event. The black hole flared dramatically, and then it went back to sleep. We don't know exactly what caused that awakening. Perhaps a large cloud of gas fell in, or maybe a star wandered too close and was partially torn apart by tidal forces. Whatever happened, it shows that the quiet we see today isn't permanent, and we have direct evidence of small-scale activity even now. Every so often, Sagittarius, a star, flares up, brief bursts of increased brightness in X-rays and infrared that last anywhere from a few minutes to a few hours before fading back to normal. These flares might be caused by small clumps of gas falling in, or by magnetic field lines snapping and reconnecting, releasing stored energy. The most dramatic of these flares happened in 2019, when Sagittarius, a star, suddenly became brighter than anyone had ever recorded, more than twice its previous maximum brightness. For a brief moment, astronomers wondered if something major was happening. Was a star being torn apart? Was a massive cloud of gas finally falling in? Follow-up observations suggested it was probably a particularly large clump of material, making its final plunge toward the event horizon. The flare faded, and the black hole returned to its usual quiet state. These occasional flickers are like a sleeping giant occasionally stirring, most of the time. Sagittarius, a star, is dormant, but it hasn't lost its capacity for drama. Given the right circumstances, the right amount of fuel falling in at the right time, it could wake up and blaze like the active black holes in distant galaxies. For now, though, we're fortunate to have such a quiet neighbor at the center of our galaxy. A more active black hole might make for more spectacular observations, but it might also make the Milky Way a more dangerous place to live. Chapter 10: The Unpredictable Flares. Let's talk more about those flares, because they represent one of the most intriguing aspects of Sagittarius, a star's behavior. And honestly, they're a bit frustrating for astronomers. You see, these brightenings happen without warning. There's no predictable schedule, no regular pattern. One moment, the galactic center is quiet and dim. The next, instruments are detecting a sudden spike in X-ray or infrared emission. And then, as quickly as it started, the flare fades away. leaving scientists scrambling to analyze whatever data they managed to capture. When a flare happens, research teams drop whatever else they're working on and point every available telescope at the galactic center. Time is precious. Some flares last only minutes. Every photon captured during these brief events carries information about what's happening in the extreme environment near the event horizon. What causes these sudden outbursts? There are several theories, and the truth might be a combination of all of them. One possibility is clumps of gas. Even in Sagittarius, a star's sparse-feeding environment, there are occasional pockets of denser material drifting around. When one of these clumps gets caught in the black hole's grip and spirals inward, it heats up dramatically, releasing a burst of radiation before vanishing past the event horizon. The rapid rise and fall in brightness suggests these events happen very close to the black hole, within a region small enough that light could cross it in just a few minutes. Another explanation involves magnetic fields. The plasma around Sagittarius, a star, is threaded with magnetic field lines that can become twisted and tangled as the gas moves in complex patterns. Sometimes these fields can snap and reconnect, a process similar to what causes solar flares on our sun. When this happens near a black hole, enormous amounts of stored magnetic energy can be released almost instantaneously, accelerating particles to extreme speeds and producing a flash of radiation. There's also the possibility of close stellar encounters. Stars occasionally pass very near Sagittarius, a star, on their elliptical orbits. During these close approaches, the star's own stellar wind, the stream of particles flowing away from its surface, can interact with the black hole's environment. Or, in more extreme cases, tidal forces could actually strip material from the star's outer layers, providing a sudden influx of fuel for the black hole. The flares we observe tend to be stronger in X-rays and infrared than in visible light. This makes sense because we're seeing radiation from extremely hot material, temperatures of tens of millions of degrees, which naturally emits at these high-energy wavelengths. But even within this pattern, there's variety. Some flares are mostly X-ray, others are dominated by infrared emission. Some last just minutes while others linger for hours. This variety suggests that multiple processes might be at work, or that the same process can unfold in different ways depending on the specific conditions. We're still trying to piece together a complete picture of what drives these events. One particularly tantalizing aspect of the flares is that they might let us probe regions very close to the event horizon. The speed at which brightness changes tells us something about the size of the emitting region. Faster changes mean smaller regions. Some flares change brightness on timescales of just minutes, suggesting the action is happening in a space comparable in size to the event horizon itself. By studying enough flares in detail, astronomers hope to map out the structure of the innermost accretion flow round Sagittarius, a star. Which regions produce the most emission? How does material move as it spirals inward? What role do magnetic fields play in channeling and heating the gas? The challenge is that flares are unpredictable. You can't schedule an observation and guarantee that one will happen. Research teams sometimes monitor Sagittarius, a star, for weeks, hoping to catch even one significant brightening event. When they do, the rush to collect data is intense, coordinating ground-based telescopes and space-based observatories to capture the flare at every wavelength from radio to X-rays. It's a waiting game, but one with potentially huge rewards. Each flare offers a glimpse into the dynamic, violent processes happening at the edge of one of the most extreme objects in the universe. Chapter 11, Magnetic Mayhem. There's an invisible player in the drama round Sagittarius, a star, that we haven't fully discussed yet: magnetic fields. We tend to think of gravity as the dominant force near a black hole, and that's certainly true. Gravity is what creates the event horizon, what pulls in matter, what shapes the orbits of nearby stars. But magnetic fields add a crucial layer of complexity to the story. You might wonder how magnetic fields can exist near a black hole. After all, doesn't the black hole swallow everything that gets close? The answer is that the black hole itself isn't generating the magnetic fields directly. They come from the plasma surrounding it. As electrically charged gas moves and swirls in the accretion flow, it drags magnetic field lines along with it. These fields get stretched, twisted, and amplified into complex structures. Near Sagittarius, a star, the magnetic fields are anything but simple or stable. They're chaotic, constantly shifting as the plasma flows, collides, and heats up. Observations using polarized light waves that have been aligned in particular directions, have revealed spiraling patterns in the faint glow around the black hole, showing that the magnetic fields are strong enough to influence how matter moves. This is where things get really interesting. Magnetic fields can actually push back against gravity. When they become tightly wound and concentrated, they can act like barriers, preventing material from falling inward as quickly as gravity alone would pull it. This might be part of the reason why Sagittarius, a star, is so quiet. The magnetic fields could be holding back a significant portion of the gas that would otherwise be feeding the black hole. But the same fields that can block material can also release tremendous energy when they snap or realign. Remember those flares we just discussed? Magnetic reconnection, the sudden breaking and rejoining of field lines, is one of the leading explanations for at least some of them. When tangled magnetic fields suddenly release their stored energy, they can heat particles to extreme temperatures and accelerate them to near light speeds, producing a burst of radiation. In other black hole systems, strong magnetic fields are responsible for launching powerful jets, beams of particles shooting out from the poles at nearly the speed of light, extending for thousands or even millions of light years into space. These jets are among the most energetic phenomena in the universe, carrying more power than entire galaxies. Sagittarius, a star, doesn't have obvious large-scale jets, at least not right now. But there are hints of smaller, weaker outflows, streams of particles being pushed away from the black hole's vicinity. If magnetic fields are responsible for these outflows, they might be acting as a kind of pressure valve, releasing energy that would otherwise build up in the accretion flow. The challenge with studying magnetic fields near a black hole is that we can't see them directly. We have to infer their presence and structure from the way they affect the light we observe. Polarization measurements are one of the best tools we have. The direction and amount of polarization tells us about the orientation and strength of the fields. Recent observations have started to give us our first real glimpse of the magnetic architecture around Sagittarius, a star. The picture that's emerging shows a complex environment where ordered and chaotic regions coexist. Close to the black hole, there seem to be some organized field structures, but farther out, everything becomes more tangled and turbulent. Understanding these magnetic fields is crucial for understanding how the black hole feeds, how it produces radiation, and why it's so quiet compared to its more active cousins. The interplay between gravity and magnetism near the event horizon is one of the most extreme examples of physics we can study, conditions we could never replicate in any laboratory on Earth. As our instruments improve and we can measure polarization more precisely, we'll get a clearer picture of this invisible architecture. The magnetic fields around Sagittarius, a star, might be hidden from direct view, but their effects are written in the light that reaches us from the heart of our galaxy. Chapter 12, the Schwarzschild Radius. Now let's get a bit more technical and talk about one of the most fundamental properties of any black hole, its Schwarzschild radius. This is essentially the size of the event horizon, and understanding it helps us grasp what we're really dealing with. When we talk about Sagittarius, a star, the concept comes from a German physicist who, in 1916, was the first to find a mathematical solution to Einstein's newly published theory of general relativity that described what we now call a black hole. His equations told us that if you compress enough mass into a small enough space, there will be a radius at which the escape velocity equals the speed of light. Inside that radius, nothing can escape. Outside, objects can still orbit, hover, or even fly away if they have enough energy. But the boundary itself, the Schwarzschild radius, marks the point of no return. Here's the beautiful thing about this concept. The Schwarzschild radius depends only on mass. If you tell me how massive an object is, I can tell you exactly how big its event horizon would be if all that mass were compressed into a black hole. The formula is surprisingly simple. For Sagittarius, a star, with its vermilion solar masses, the Schwarzschild radius works out to about 12 million kilometers. That's roughly 17 times the Sun's diameter. To put it another way, you could fit several copies of our Sun lined up side by side within the event horizon of our galaxy's central black hole. 12 million kilometers sounds enormous, and by human standards it absolutely is. You could drive a car at highway speed for millions of years and still not cover that distance. But in cosmic terms, it's remarkably compact. The black hole contains 4,000,000 times the mass of the Sun, but occupies a sphere only 17 times larger. If the Sun had the same density, it would be almost microscopic. This extreme compactness is what makes the gravity so intense. Everything inside that 12 million kilometer sphere is cut off from the rest of the universe forever. Light emitted inside cannot escape. Matter that crosses the boundary continues falling inward until, well, we don't really know. The mathematics says it reaches a singularity, a point of infinite density, where our known physics breaks down. But many physicists suspect something else happens, something that we'll only understand once we have a working theory of quantum gravity. What we can study is the region just outside the event horizon, and that's where much of the exciting physics happens. This is where the accretion flow spirals inward, where magnetic fields twist and snap, where particles accelerate to near-light speeds. It's also where the predictions of general relativity can be tested in their most extreme form. The Schwarzschild radius has become something we can actually observe, at least indirectly. When images of black holes were created by linking radio telescopes around the world, what they showed was a bright ring of light surrounding a dark central shadow. That shadow is directly related to the event horizon. It's the region where light gets bent so much that it falls into the black hole rather than reaching our telescopes. The actual event horizon is a bit smaller than the shadow's edge, but the relationship is precise enough that measuring the shadow tells us the mass of the black hole. And when astronomers did this for Sagittarius, a star, the size they measured matched almost perfectly with what the orbits of nearby stars had already told us. The black hole has exactly the properties that general relativity predicts. This consistency is important because it confirms that our understanding of gravity holds up, even in these extreme conditions. Einstein's theory, developed over a century ago using thought experiments and mathematical elegance, continues to pass every test we throw at it. Near a black hole's event horizon, where spacetime is curved so severely that common sense breaks down, the equations still work. Of course, there are limits to our testing. We can probe the region near the event horizon, but we can't see beyond it. The Schwarzschild radius marks a fundamental barrier to observation. Whatever happens inside is, by definition, unknowable to us through any signal or measurement. This is part of what makes black holes so fascinating. They're the universe's perfect hiding places, keeping secrets that may be forever beyond our reach. Chapter 13, Seeing the Unseeable. For decades, astronomers studied Sagittarius, a star, indirectly, tracking the orbits of nearby stars, measuring faint radio emissions, catching occasional flares. But there was one goal that seemed almost impossible: actually taking a picture of the black hole itself. Think about the challenges involved. The black hole is 26,000 light-years away, even though its event horizon spans 12 million kilometers. From Earth, that appears incredibly tiny, roughly the size of a donut, sitting on the surface of the Moon, as seen from Earth. No single telescope on the planet could possibly resolve something that small. And yet, in 2022, a global collaboration of scientists revealed the first image of Sagittarius, a star's shadow. How did they do it? The key is a technique called very long baseline interferometry. Instead of building one impossibly large telescope, you link together many smaller telescopes spread across the globe. Each telescope records the radio signals from the target, along with incredibly precise timing information provided by atomic clocks. Later, these recordings are combined using sophisticated algorithms to produce an image with the resolutio n of a virtual telescope as big as the distance between the individual dishes. For imaging a black hole, You essentially need a telescope the size of Earth. And that's exactly what this project created. Radio observatories on multiple continents and even at the South Pole were coordinated to observe Sagittarius A star simultaneously. Each location captured its own slice of the incoming radio waves. The raw data, we're talking petabytes of information, was stored on special hard drives and physically shipped to processing centers because no internet connection could handle the volume. Then came the hard part, combining all that data into a coherent image. This required not just computational power, but also sophisticated algorithms that could fill in gaps in the coverage and account for all the ways the signals could be distorted or misaligned. For Sagittarius A star, there was an additional complication that made it even harder to image than other black holes. The material orbiting our galactic black hole moves extremely fast. Some of it completes an orbit in just minutes. This means the brightness pattern around the black hole changes constantly during the observation. It's like trying to take a long exposure photograph of a spinning top. Everything blurs together. The team had to develop new techniques to handle this variability. Instead of producing a single sharp image, they generated thousands of possible images consistent with the data and looked for features that remained stable across all of them. The result was an averaged view, a composite that showed the consistent structure underlying all the rapid changes. When the image was finally released, it showed exactly what theory predicted: a bright ring of radio emission surrounding a dark central shadow. The ring was slightly lopsided, brighter on one side than the other. Due to relativistic effects, gas moving toward us appears brighter because of the way high-speed motion affects light. The dark center was not the black hole itself, but its shadow, the region where light gets bent so severely that it falls in, rather than escaping to our telescopes. The actual event horizon sits just inside this shadow. It was a blurry picture, to be sure, not the crisp, colorful images we're used to seeing from other space telescopes. But consider what it represents: direct visual confirmation of a supermassive black hole at the center of our galaxy. Something that just a few decades ago was theoretical, inferred only from the movements of stars, was now captured in an actual image. This achievement built on an earlier success with a different black hole, the one at the center of a galaxy 55 million light-years away. That black hole was photographed first, even though it's much farther away, because it's also much larger. Its greater size means the material around it moves more slowly, making it easier to capture a stable image. Sagittarius A star, despite being closer, was the harder target. Its successful imaging represented a triumph of technology, cooperation, and persistence. Scientists from around the world worked together for years, developing new techniques and pushing the boundaries of what was possible. And this is just the beginning. Future observations will add more telescopes to the network, improving both resolution and sensitivity. We might eventually be able to watch the material around Sagittarius A star in real time, creating movies of gas spiraling toward the event horizon. The unseeable is becoming increasingly visible. Chapter 14, The Missing Accretion Disk. When you see illustrations of black holes in popular media, they usually show a dramatic, glowing disk of material swirling around the event horizon like water going down a drain. These accretion disks can be spectacularly bright, the most luminous objects in the universe, in some cases. So when astronomers looked at Sagittarius A star, one of the mysteries was, where's the disk? Oh, there's material there, but it's nothing like the blazing accretion disks around active black holes in distant galaxies. The emission from Sagittarius A star is faint and irregular, far dimmer than what you'd expect given its mass. The answer goes back to what we discussed earlier about why our galactic black hole is so quiet. There's simply not enough fuel. For a bright accretion disk to form, you need a steady, substantial flow of material falling toward the black hole. This material gets compressed and heated as it spirals inward, creating the characteristic glow. But the environment around Sagittarius A star is relatively sparse. Yes, there are stars nearby, but they're mostly in stable orbits that don't shed much material toward the center. Gas clouds do pass through the region, but they're not dense enough to form a thick, bright disk. What we see instead is something called a radiatively inefficient accretion flow. The gas around the black hole is there, but it's thin and spread out. It doesn't compress tightly enough to heat up dramatically. Much of it swirls around for a while and then gets pushed back out by magnetic fields and turbulence before ever reaching the event horizon. Think of it like trying to start a fire with wet wood. The material is there, but the conditions aren't right for a robust blaze. You might get some smoldering and the occasional spark, but not the roaring flames you'd get with dry kindling and proper airflow. There's evidence that this wasn't always the case. Those light echoes we discussed earlier suggest that just a few hundred years ago, a blink of an eye in cosmic terms, Sagittarius' star was much brighter. Something fed it a substantial meal, and it flared up dramatically. Then the food ran out, and it went back to its current dim state. This episodic behavior seems to be typical for supermassive black holes. They're not constantly feeding. Instead, they go through phases of activity and dormancy, depending on what's happening in their environment. When there's lots of gas available, perhaps during a galaxy merger, or when a large cloud drifts through the central region, the black hole can light up spectacularly. During quiet times when fuel is scarce, they fade to near invisibility. Right now, Sagittarius' star is in one of these quiet phases. Its accretion disk is really just as sparse, disorganized flow of hot gas that produces weak radio emission and occasional flares. It's a far cry from the dramatic structures we see around more active black holes. But that doesn't mean it's boring. The faintness actually makes Sagittarius a star an excellent laboratory for studying how black holes behave when they're not overwhelming their surroundings with radiation. We can probe the detailed structure of the accretion flow, watch individual flares and outbursts, and test our theoretical models in ways that would be impossible with a more active system. And there's always the possibility that things could change. A large gas cloud, a star that wanders too close, or the eventual collision with the Andromeda galaxy could all potentially wake up our galactic black hole and transform it into something much more dramatic. Chapter 15. Technologies that opened our eyes. The discovery and study of Sagittarius' star is really a story about the evolution of our tools. Each generation of technology has revealed something new about the hidden heart of our galaxy. Let's trace that journey through some of the key breakthroughs. The story starts with radio astronomy in the 1930s and 40s. The accidental discovery that radio waves could be detected from space opened an entirely new window on the universe. Suddenly, objects that were invisible to optical telescopes could be studied. The strong radio source at the galactic center was among the first celestial objects discovered this way. Through the 50s and 60s, radio telescopes grew larger and more sensitive. Scientists developed techniques to combine signals from multiple antennas, improving their ability to pinpoint exactly where radio emissions were coming from. The radio source at our galaxy's center was revealed to be remarkably compact, not a diffuse cloud, but a concentrated point. Then came infrared astronomy. By the 1980s and 90s, telescopes sensitive to infrared light were giving us our first clear views through the dust that had blocked optical observations for so long. Mountains in Hawaii and Chile, where the air is dry and thin, became home to powerful infrared observatories. The real breakthrough for Sagittarius' star came with adaptive optics. This technology, which uses flexible mirrors and laser guide stars to compensate for atmospheric distortion, transformed ground-based astronomy. Images that had been blurry suddenly became sharp. Individual stars near the galactic center could be distinguished and tracked. Space-based observatories added another dimension. Telescopes orbiting above Earth's atmosphere didn't have to deal with atmospheric distortion at all. They could observe in wavelengths that don't penetrate the atmosphere, like X-rays and certain infrared bands. These space telescopes caught Sagittarius' star's occasional flares and helped map the environment around the black hole. X-ray observatories launched around the turn of the millennium revealed a galactic center that was mostly quiet but occasionally active. They detected faint emission from hot gas near the black hole and caught the brief X-ray flares that signaled feeding events. Infrared space telescopes mapped the crowded starfields and warm dust of the central region with unprecedented clarity. They helped astronomers understand the structure of the environment in which Sagittarius, a star, exists. And then came the planet-sized virtual telescope. By linking radio observatories across the globe, scientists created an instrument capable of resolving the shadow of a black hole's event horizon. This required not just large dishes, but atomic clocks accurate to billionths of a second, massive data storage systems, and years of processing time to combine the observations. Each of these technologies built on what came before. Radio astronomy laid the groundwork. Infrared broke through the dust barrier. Adaptive optics sharpened ground-based images. Space telescopes freed us from atmospheric limitations. And global interferometry achieved resolutions that would have seemed impossible just a few decades ago. The story continues. Next-generation space telescopes are now studying the galactic center with even greater sensitivity. Plans are underway to extend the global radio network with additional stations and even potential space-based dishes. New instruments sensitive to gravitational waves might eventually detect the signals. From matter spiraling into supermassive black holes, every advance in technology has brought new discoveries about Sagittarius, a star. There's every reason to believe that trend will continue. The mysteries we're puzzling over today, the exact nature of the accretion flow, the spin of the black hole, the structure of the magnetic fields, may be answered by instruments that haven't been built yet. In a sense, the history of studying our galactic black hole is a history of human ingenuity. We can't travel to the center of the galaxy. We can only observe from our cosmic neighborhood 26,000 light-years away. But by developing ever more clever ways to capture and analyze the signals reaching us, we've managed to turn that distant, hidden object into one of the best-studied supermassive black holes in the universe. Chapter 16, Gravitational Lensing, the Universe as a Magnifying Glass. One of the most fascinating tools nature has given us for studying black holes doesn't require building anything at all. It's called gravitational lensing, and it's a direct consequence of Einstein's discovery that massive objects bend space, and therefore bend light. You know how a regular glass lens focuses light by bending it as it passes through? Gravity can do the same thing, but on a cosmic scale. When light from a distant object passes near something massive, like a star, a galaxy, or a black hole, the curvature of space around that mass deflects the light's path. The massive object acts like a natural lens, magnifying and distorting whatever is behind it. This phenomenon occurs throughout the universe, and it's useful for studying all kinds of cosmic objects. But it's especially interesting when applied to black holes, because black holes warp space more severely than almost anything else. When light passes near Sagittarius, a star, it doesn't travel in a straight line. The intense gravity bends it, sometimes sending it curving around the black hole before continuing on to reach our telescopes. This bending creates effects that can be observed and measured. For example, background stars that pass behind or very close to Sagittarius, a star, from our point of view can appear briefly magnified. This is called gravitational microlensing. As the alignment changes due to orbital motion, the magnification fades. By carefully monitoring these events, astronomers can confirm the mass of the black hole and probe the structure of the space around it. The black hole also bends its own light, or rather, the light from the hot gas swirling around it. Some of this light gets bent so much that it orbits the black hole before escaping, creating that bright ring we see in images. The exact size and shape of this ring depend on the black hole's mass and how severely it warps spacetime. In principle, gravitational lensing could help us see things that would otherwise be invisible. Light from the far side of the black hole's accretion flow, which would normally be blocked from our view, can be bent around and redirected toward us. This gives us information about regions we couldn't observe directly. There's even a theoretical concept called a photon sphere, a region around a black hole, where gravity is so strong that photons can orbit in circles. Light at this boundary is precariously balanced between falling in and escaping. Any light that happens to circle here and then gets kicked outward contributes to what we observe. The challenge with using gravitational lensing to study Sagittarius, a star, is that the alignments needed for strong effects are rare and often brief. The galactic center is crowded with stars, but they have to pass close enough to the black hole, from our perspective, to produce measurable lensing. These events can last hours to days and require careful monitoring to catch. When they do happen, though, they provide unique information. The way light is bent tells us about the geometry of space near the event horizon. Deviations from what general relativity predicts could indicate new physics, though so far, everything we've observed matches Einstein's predictions remarkably well. In the future, as our instruments become more sensitive and our monitoring more continuous, gravitational lensing may become an increasingly powerful tool for studying Sagittarius, a star. The universe has given us this natural magnifying glass. We just need to become better at using it. Chapter 17. What we still don't know. Despite all our advances in observing Sagittarius, a star, there's an enormous amount we still don't understand. Let me walk you through some of the biggest remaining mysteries. First, there's the question of spin. Black holes aren't just defined by their mass. They can also rotate. A spinning black hole drags space-time around with it in a phenomenon called frame dragging. The spin affects how matter falls in, the size and shape of the innermost orbits, and potentially the power of any jets or outflows. For Sagittarius, a star, we don't know the spin with any precision. Theoretical models predict it should be spinning, probably fairly rapidly, but measuring that spin requires observations we haven't been able to make yet. Polarization studies of X-rays and more detailed imaging of the accretion flow might eventually pin it down. Related to spin is the question of orientation. The black hole's rotation axis points in some direction, but which? For black holes that produce large jets, this is easy to determine. The jets point along the spin axis. But Sagittarius, a star, doesn't have obvious jets, so we're left guessing. Knowing the orientation would tell us a lot about the history of the black hole. If the spin axis is aligned with the plane of the galaxy, it suggests the black hole grew mainly by pulling in material from the galactic disk. If it's tilted at a strange angle, that might indicate past mergers with other black holes that came in from random directions. Then there's the structure of the magnetic fields we discussed earlier. We know they're there, and we know they're important, but the detailed geometry, how the field lines are shaped, how strong they are at different distances from the event horizon, how they change over time, remains unclear. Better polarization measurements will help, but we're still limited by the resolution and sensitivity of our instruments. The feeding behavior of Sagittarius, a star, is another mystery. Why is it so quiet now? What triggered the apparent outburst a few hundred years ago? Is there a reservoir of gas building up somewhere that will eventually fall in and wake the black hole up again? Understanding the long-term feeding cycle requires observations over timescales longer than any individual astronomer's career. Inside the event horizon is, of course, the ultimate mystery, one that may be fundamentally unsolvable. We know matter falls in, but we don't know what happens to it. Does it reach a true singularity of infinite density? Or does quantum mechanics prevent that, creating something else entirely? This question touches on some of the deepest problems in physics, involving the intersection of gravity and quantum mechanics that we still don't know how to handle. And then there are the existential questions. Is Sagittarius, a star, truly a black hole as general relativity describes? Or could it be something more exotic? A few theorists have proposed alternatives. Objects that would look almost exactly like black holes from the outside, but have subtle differences. Things like gravastars, boson stars, or fuzzballs from string theory. These alternatives are considered highly unlikely, but ruling them out definitively requires more precise observations than we've made so far. Each of these mysteries represents an opportunity for future discovery. As our tools improve and our understanding deepens, some of these questions will be answered. And inevitably, the answers will raise new questions we haven't even thought of yet. That's how science works. Every answer is also a doorway to new mysteries. Chapter 18. Could anything orbit inside the event horizon? Here's a question that might seem philosophical, but actually has deep physical significance. What happens inside a black hole? Could there be anything, matter, energy, Structures of any kind orbiting within the event horizon? From the perspective of classical physics, the answer is a definitive no. Once something crosses the event horizon, it is committed to falling toward the singularity at the center. Space and time become so warped inside a black hole that all paths lead inward. There's no possible orbit, no way to circle round. Because there's no round to circle, every direction eventually points toward the singularity. To understand this, you have to appreciate how profoundly space and time are distorted inside a black hole. Outside, we experience space as having 3 dimensions we can move through freely, and time as a single dimension that flows inexorably forward. Inside the event horizon, this relationship breaks down. Space and time essentially swap roles. Moving forward in time becomes equivalent to moving toward the singularity. You can no more avoid the singularity than you can avoid tomorrow. So from classical general relativity's perspective, there are no orbits inside a black hole. There's only falling. But physics isn't finished. Classical general relativity breaks down at the singularity, producing infinities that don't make physical sense. Most physicists believe that a complete theory, one that combines gravity with quantum mechanics, would resolve these infinities and tell us what really happens inside. Some speculative ideas offer tantalizing possibilities. In loop quantum gravity, space is made up of discrete chunks rather than being smoothly continuous. When matter collapses, this granular structure might prevent a true singularity from forming. Instead, the matter might bounce and oscillate in some way, potentially creating complex dynamics inside the horizon. String theory suggests black hole interiors might be filled with fundamental strings in exotic configurations. The concept of fuzzballs proposes that what we think of as an empty region inside the event horizon is actually stuffed with quantum information encoded in tangled strings. If so, there might be structure and activity inside that we simply can't perceive from outside. Some solutions to Einstein's equations allow for structures called Kerr black holes, rotating black holes that have an inner horizon and possibly a ring-shaped singularity, rather than a point. In the mathematical idealization, regions inside such a black hole could in principle support closed time-like curves, paths, that loop back on themselves in time. These are probably not physical. Perturbations would likely destroy such delicate structures, but they hint at how strange the interior might be. There are even more exotic proposals. Some physicists have suggested that black hole interiors might be gateways to other regions of spacetime, or even other universes. The famous idea of wormholes, tunnels through spacetime connecting distant points, originated from studying black hole mathematics. The problem with all these ideas is that they're fundamentally untestable, at least for now. The event horizon is an absolute barrier to information. Whatever happens inside cannot be communicated to the outside universe. We can speculate, we can calculate, but we can't observe. For Sagittarius, a star specifically, the question of what's inside its event horizon is the ultimate mystery. For millions solar masses of material have fallen into this object over billions of years. Where did it all go? Is it compressed into a point of infinite density? Is it stored as quantum information on the horizon itself? Is it occupying some structure we can't even conceptualize? We may never know, and perhaps there's something fitting about that. In a universe full of mysteries we're steadily solving, the inside of a black hole might remain forever beyond our reach, a reminder that there are limits to what can be known. Chapter 19, Dark Matter and Alternative Theories. While the evidence for Sagittarius, a star, being a supermassive black hole is overwhelming, good science means considering alternatives. What if it's something else entirely? What if our understanding is incomplete? One alternative that's been proposed is dark matter. We know dark matter exists. Its gravitational effects are visible throughout the universe, holding galaxies together and shaping the large-scale structure of the cosmos. But we don't know what it's made of. Could the object at the center of our galaxy be an incredibly dense concentration of dark matter, rather than a black hole? The problem with this idea is that dark matter, as far as we understand it, doesn't interact with itself strongly enough to collapse into such a dense configuration. Normal matter can collapse because it can radiate energy away. As gas falls and compresses, it heats up and releases that heat as radiation, allowing it to compress further. Dark matter doesn't radiate efficiently, so it tends to stay spread out in large halos rather than collapsing into compact objects. To make a dark matter explanation work for Sagittarius A star, you'd need some new kind of dark matter with properties very different from what we currently observe elsewhere. That's possible in principle, but it would be a dramatic departure from our standard model. Another alternative is something called a boson star. Bosons are particles that follow different quantum rules than the fermions, electrons, protons, neutrons that make up ordinary matter. Photons are bosons. The Higgs particle is a boson. Some theories propose the existence of very light, stable bosons that could clump together into star-like objects. A boson star wouldn't have a true event horizon or a singularity. It would be a fuzzy ball of quantum particles held together by its own gravity. From the outside, it might look very similar to a black hole, bending light, pulling on nearby stars, producing a dark shadow at its center. But the details of its behavior could differ in subtle ways. The challenge is that no observation so far has shown these subtle differences. The size of Sagittarius A star's shadow, the orbits of nearby stars, the properties of its accretion flow, all of these match what we expect from a black hole, according to general relativity. If it's something else, it's doing a very good impression. There's also the gravistar hypothesis. This idea proposes that what we call a black hole is actually a shell of exotic matter, surrounding a core of dark energy, the same mysterious stuff that's causing the universe's expansion to accelerate. A gravistar would have no singularity and no true event horizon, just a very thin layer that looks like one from the outside. Like the boson star, a gravistar would closely mimic a black hole's observable properties. The differences would only show up in very precise measurements of how it interacts with infalling matter or gravitational waves. More exotic ideas from theoretical physics include fuzzballs from string theory, firewall scenarios from debates about information in black holes, and various proposals involving extra dimensions or modified gravity. Each of these would have slightly different observable consequences, but detecting those consequences would require much more sensitive instruments than we currently have. For now, the black hole interpretation remains the overwhelming favorite. It fits all the data, requires no modifications to established physics, and matches what we observe at the centers of other galaxies. But scientists keep testing, keep probing, keep looking for any hint that our understanding might be incomplete. That's not because anyone seriously expects to disprove the black hole model. It's because testing theories at their limits is how science advances. Even if every test confirms our current understanding, the process of testing refines that understanding and increases our confidence in it. And if any test ever showed something unexpected, well, that would be one of the most exciting discoveries in the history of physics. Chapter 20. How did Sagittarius A star shape our galaxy? Here's a question that might not occur to you at first. Did the black hole at the center of our galaxy help create the galaxy we live in today? Could Sagittarius A star have influenced the structure, history, and even habitability of the Milky Way? The short answer is yes. Probably. But we're still working out the details. Let's start with what we know about the relationship between supermassive black holes and their host galaxies. One of the most striking discoveries in modern astronomy is that there's a tight correlation between the mass of a galaxy's central black hole and the mass of its central bulge, the dense, spherical collection of stars in the galaxy's core. This correlation holds across a huge range of galaxy sizes. Small galaxies have small bulges and small black holes. Giant galaxies have massive bulges and enormous black holes. The relationship is so consistent that it suggests black holes and galaxies somehow grow together, influencing each other's development. How does this influence work? One mechanism is called AGN feedback, AGN standing for active galactic nucleus. When a supermassive black hole is actively feeding, it doesn't just passively consume matter. It releases enormous amounts of energy as radiation and, in many cases, powerful jets of particles shooting out from its poles. This energy output can have dramatic effects on the surrounding galaxy. It can heat gas clouds, preventing them from collapsing to form new stars. It can blow gas out of the galaxy entirely, depriving future star formation of raw material. In some galaxies, active black holes appear to regulate star formation, creating a feedback loop where the black hole's activity and the galaxy's growth are intimately connected. Did Sagittarius A star do this for the Milky Way? We don't see obvious signs of strong AGN feedback in our galaxy today. Sagittarius A star is too quiet, its energy output too low, to significantly affect star formation anywhere except in its immediate vicinity. But that hasn't always been the case. There are tantalizing hints that our galactic black hole was more active in the past. The Fermi bubbles, enormous structures of high-energy emission extending above and below the galactic plane, suggest that something at the center of the Milky Way released a huge amount of energy within the past few million years. If Sagittarius A star went through an active phase, even briefly, it could have left these bubbles as remnants. Going further back to the early history of our galaxy, things are even more uncertain but potentially more significant. The Milky Way was built through the gradual merging of smaller protogalaxies over billions of years. During these merger events, gas would have been funneled toward the center, potentially triggering episodes of intense black hole feeding. These active phases could have influenced how the galaxy's central bulge formed. The energy released by the growing black hole might have heated and redistributed gas, affecting where and when stars formed. Without the black hole, the Milky Way's inner structure might look quite different. There's also the question of the Milky Way's spiral structure. Our galaxy has beautiful spiral arms stretching out from a central bar. The black hole's gravity dominates only in the innermost region, so it doesn't directly shape the outer spiral pattern. But the dense central mass concentration, including both the black hole and the dense star cluster around it, might help stabilize the bar structure, which in turn channels gas inward and influences the galaxy's overall dynamics. Some researchers have speculated about even more indirect influences. If Sagittarius A star went through a particularly active phase billions of years ago, the radiation produced could potentially have affected planetary atmospheres throughout a significant portion of the galaxy. Exactly how significant this effect would be is debated, but it's an intriguing thought that the black hole at the galaxy's center could have played a role in the conditions that allowed life to develop. We're still learning about these connections. The fossil record of Sagittarius A star's activity is written in the chemical abundances of stars, the structure of the central region, and the echoes of ancient outbursts still propagating through the galaxy. Reading that record requires both precise observations and sophisticated simulations that can model billions of years of galactic evolution. What seems clear is that Sagittarius A star isn't just a passive resident at the galaxy's center. It's part of the Milky Way's story. How much of a part remains to be determined. Chapter 21. The Next Generation of Black Hole Science. The image of Sagittarius A star that captured the world's attention wasn't an ending. It was a beginning. Scientists are already working on the next generation of instruments and techniques that will take us even deeper into the mysteries of our galactic black hole. The global network of radio telescopes that produced the first image is being expanded. New stations are being added in Africa, which will improve coverage of the southern sky. There are proposals for dishes in the Pacific Islands and potentially even floating platforms at sea. Each new location helps fill in gaps in the virtual planet-sized telescope, improving both resolution and sensitivity. But the most dramatic improvement might come from moving into space. Ground-based telescopes, no matter how sophisticated, still have to deal with Earth's atmosphere and the limited baselines available on our planet's surface. A radio telescope in orbit, linked to ground stations, would create baselines much longer than Earth's diameter, potentially dramatically increasing the resolution of the images. Several space agencies are studying concepts for space-based radio interferometry. The engineering challenges are substantial. You need incredibly precise positioning and timing for the spacecraft, robust communication links, and ways to combine data from ground and space that introduce no errors. But the potential scientific payoff is huge. With sharper images, we might be able to watch material move around Sagittarius' star in something approaching real time. Instead of averaging over hours or days to produce a static image, we could track bright spots as they orbit, measure how they change, and see the dynamics of the innermost accretion flow directly. Polarimetry, measuring the orientation of light waves, is another frontier. Different physical processes produce different patterns of polarization. So detailed polarization maps can reveal the structure of magnetic fields and the nature of emission mechanisms near the black hole. Space-based and ground-based X-ray observatories are being equipped with polarimeters that will probe these properties in high-energy light. Gravitational wave astronomy represents an entirely different approach so far. Ground-based gravitational wave detectors have observed collisions between stellar mass black holes and neutron stars, but the gravitational waves from activity around supermassive black holes have frequencies too low for current ground-based instruments. Space-based gravitational wave observatories are in development. These missions would deploy spacecraft millions of kilometers apart, using laser beams to detect the stretching and squeezing of space caused by passing gravitational waves. Such an observatory could, in principle, detect the signal of a small object spiraling into Sagittarius' star, providing completely new information about the black hole's mass, spin, and the geometry of spacetime near its event horizon. Multi-wavelength coordination is becoming increasingly sophisticated. When something interesting happens near Sagittarius' star, a flare, an unusual pattern of activity, a gravitational wave candidate, the astronomical community can now respond rapidly. Training radio, infrared, optical, and X-ray telescopes on the target within hours or even minutes. This kind of coordinated observation captures phenomena across the electromagnetic spectrum, providing a complete picture that any single instrument would miss. Machine learning and artificial intelligence are also playing growing roles. The data volumes from modern telescopes are enormous, far more than humans could analyze manually. AI systems can scan through this data looking for interesting signals, classify different types of events, and even help reconstruct images from interferometric data. These tools will become increasingly important as our observations become more detailed and more continuous. The next decade should bring dramatic advances. We might measure Sagittarius' star's spin. We might see polarization maps that reveal its magnetic field structure. We might catch the gravitational wave signal from something spiraling into it. We might even make movies of gas swirling toward the event horizon. Each advance will answer some questions and raise others. That's the nature of exploration. The more we learn about the black hole at the center of our galaxy, the more we realize how much we still don't understand. Chapter 22, X-ray polarimetry and the hunt for spin. Let's go deeper into one of the most promising techniques for learning more about Sagittarius' star, X-ray polarimetry. You've probably seen images of light through polarized sunglasses. The lenses block light waves that are oscillating in certain directions, reducing glare and making certain things easier to see. Polarization is a fundamental property of light waves. They oscillate in particular directions, and various physical processes can align those oscillations in predictable ways. When matter falls toward a black hole and heats up to millions of degrees, it emits X-rays. These X-rays carry information about the conditions where they were produced, including the magnetic field structure and the geometry of the emitting region. If we can measure the polarization of these X-rays, we can decode that information. Here's where it gets really interesting. The spin of a black hole affects how space and time are warped around it. A rotating black hole drags spacetime itself into a swirling pattern. Light passing through this warped region gets its polarization modified in characteristic ways. By carefully measuring X-ray polarization from Sagittarius' star, especially during flares when the emission is stronger, astronomers hope to detect the signature of frame dragging. This would tell us how fast the black hole is rotating, a quantity that's extremely difficult to measure any other way. The challenge is that X-ray polarimetry is really hard. Regular X-ray telescopes just measure the energy and direction of incoming photons. To measure polarization, you need specialized detectors that can also determine the orientation of each photon's electric field. A dedicated X-ray polarimetry mission launched recently has started collecting data on various cosmic objects. Sagittarius A* is a challenging target because it's relatively faint in X-rays most of the time. But during flares, there might be enough signal for a measurement. The spin of Sagittarius A* would tell us a lot about its history. If it's spinning rapidly in the same direction as the galaxy's rotation, that suggests it grew mainly by accreting material from the galactic disk over long periods. If its spin is slow or tilted at a strange angle, that might indicate chaotic growth from random directions, or past mergers with other black holes that came in from different angles. Spin also matters for understanding the black hole's potential as an energy source. Rotating black holes can, in principle, give up some of their rotational energy to power jets and other energetic outflows. If Sagittarius A* is spinning rapidly, it might have a substantial reservoir of energy that could be tapped under the right circumstances. Of course, spin is just one piece of the puzzle. X-ray polarimetry can also probe the structure of the accretion flow, how the hot gas is distributed, how it moves, what magnetic fields it contains. Combined with radio observations and optical, infrared monitoring, these measurements build toward a complete three-dimensional picture of the black hole's environment. We're still in the early days of this work. The first X-ray polarimetry satellites have limited sensitivity, and Sagittarius A* requires catching it during a flare to get good data. Future, more powerful instruments will be able to do more continuous monitoring and detect fainter signals. But the potential is enormous. X-ray polarimetry might be the key to measuring black hole spin, one of the most fundamental properties that has remained elusive. Through other observational techniques. Chapter 23, Listening for Gravitational Waves. So far, we've talked about observing Sagittarius A* with various forms of light, radio waves, infrared, visible, X-rays. But there's another way to detect black holes that doesn't involve light at all: gravitational waves. Gravitational waves are ripples in the fabric of spacetime itself. When massive objects accelerate, especially when they're moving rapidly and close together, they send out these waves at the speed of light. The waves stretch and squeeze space as they pass through, and with sensitive enough instruments, we can detect that stretching and squeezing. Ground-based gravitational wave observatories have already detected dozens of events, mostly mergers of stellar mass black holes and neutron stars. These detections have opened a completely new window on the universe, allowing us to study objects and events that produce little or no electromagnetic radiation. But the gravitational waves from those detected events have relatively high frequencies, the kind produced by compact objects spiraling together in their final moments. Sagittarius A*, being millions of times more massive, would produce gravitational waves at much lower frequencies, so low that ground-based detectors can't hear them. What kind of event would produce detectable gravitational waves from Sagittarius A*? The most promising scenario is something called an extreme mass ratio in spiral, or EMRI. This is when a much smaller object, a stellar mass black hole, neutron star, or even a regular star, gets captured into an orbit around the supermassive black hole and slowly spirals inward over thousands of years. As the smaller object orbits, it continuously radiates gravitational waves, gradually losing energy and sinking closer to the event horizon. The gravitational wave signal encodes detailed information about the spacetime geometry around the supermassive black hole, its mass, spin, and even potential deviations from general relativity's predictions. Detecting an EMRI requires a space-based gravitational wave observatory. Space-based missions in development would deploy multiple spacecraft, separated by millions of kilometers, using lasers to measure the tiny distance changes caused by passing gravitational waves. Such an observatory could detect EMRs from supermassive black holes throughout the universe, including potentially from Sagittarius A*. If we ever detected a gravitational wave signal from something spiraling into our galactic black hole, it would be revolutionary. we'd be able to measure Sagittarius A's spin with incredible precision. We'd test general relativity in the strong gravity regime with unprecedented accuracy. We'd learn about the population of compact objects orbiting near the galactic center. The challenge is that these space missions are technically demanding and won't launch for at least another decade. In the meantime, we continue to study Sagittarius A* with light and prepare for the day when we might hear it. With gravity, there are also pulsar timing arrays, networks of pulsars spinning neutron stars, with precise radio pulses scattered throughout the galaxy. By monitoring the exact arrival times of pulsar signals, astronomers can potentially detect very low-frequency gravitational waves from the largest supermassive black hole binaries in the universe. These techniques are already being used and have recently reported evidence for a background hum of gravitational waves from many distant sources. Whether they'll ever be sensitive enough to study Sagittarius A* specifically remains to be seen. Gravitational wave astronomy and electromagnetic astronomy are increasingly complementary. When we can observe the same object or event with both light and gravitational waves, we get a much more complete picture than either method alone would provide. For supermassive black holes like Sagittarius A*, that multi-messenger future holds incredible promise. Chapter 24, When Galaxies Collide. Now let's look billions of years into the future, to an event that will transform our galaxy and wake up Sagittarius A* like nothing else in cosmic history. The collision with the Andromeda Galaxy. Right now, the Andromeda Galaxy is about 2.5 million light-years away, the most distant object, visible to the naked eye on a clear, dark night. It looks like a faint smudge of light, but it's actually a spiral galaxy even larger than our own Milky Way, containing roughly 1 trillion stars, and it's headed our way. Andromeda is approaching the Milky Way at about 110 kilometers per second. That sounds fast, and in human terms it is. It's about 400,000 kilometers per hour. But across millions of light-years of space, that speed translates to a very slow approach. It will take about 4.5 billion years for the two galaxies to actually meet. When they do, the results will be spectacular, though not quite what you might imagine from the word collision. Stars won't crash into each other, even in the densest parts of galaxies. Stars are so far apart that direct collisions are incredibly rare. If the Sun were the size of a grain of sand, the nearest star would be several kilometers away. During the galaxy collision, stars will mostly pass through the spaces between other stars. What will be dramatic is the gravitational interaction. The two galaxies will disturb each other's structure profoundly. Spiral arms will be stretched and distorted. Stars will be flung into new orbits. Some will be ejected from the combined system entirely, sent flying off into intergalactic space. Over hundreds of millions of years, the two galaxies will pass through each other multiple times, getting more entangled with each pass until they eventually merge into a single larger galaxy. Simulations suggest this merged galaxy will be an elliptical shape, more like a giant spherical blob than the beautiful spiral structures we see today. At the center of each galaxy lurks a supermassive black hole, Sagittarius A* in the Milky Way, and a similar monster in Andromeda often called M31's black hole. What happens to these black holes during the merger? At first, nothing obvious. The black holes are tiny compared to the galaxies they inhabit, gravitationally dominant in their immediate surroundings, but insignificant on the galactic scale. When the galaxies first interact, the black holes continue orbiting within their respective stellar systems, barely noticing the cosmic drama playing out around them. But gradually, over millions of years, things change. As the galaxies merge, their central regions sink toward the combined gravitational center. The two black holes, each surrounded by dense clusters of stars, spiral inward through a process called dynamical friction. They transfer orbital energy to surrounding stars, gradually losing speed and falling deeper into the merged galaxy's core. Eventually, after perhaps 100 million years or more, the two black holes find themselves in close proximity. They begin orbiting each other directly, forming a binary supermassive black hole system. This is where things get really interesting. As the two black holes orbit each other, They radiate gravitational waves, ripples in spacetime, that carry energy away from the system. This causes the black holes to spiral closer together, orbiting faster and radiating even more gravitational waves. The process accelerates, and in the final moments, the two event horizons rush together and merge. The gravitational wave signal from this merger would be one of the most powerful events in the universe, though at frequencies too low for current detectors and lasting for a cosmically brief moment. The merged black hole would be significantly larger than either of its parents, perhaps approaching 100 million solar masses or more. But before the final merger, during the long period when the two black holes are orbiting close to each other, the entire central region of the merged galaxy would be stirred up dramatically. Stars would be scattered, gas would be funneled inward, and both black holes would likely feed voraciously. This is when Sagittarius, a star, might finally wake up. The chaos of the merger would deliver huge amounts of gas to its doorstep. After billions of years of quiet dormancy, our galactic black hole could blaze to life as a quasar, its accretion disk glowing with the light of a trillion suns, its jets punching through the galactic halo and streaming out into intergalactic space. If any planets with life survive until this time, a big if, given the sun's evolution and other factors, they would witness one of the most dramatic transformations imaginable. The familiar night sky would give way to a brilliant new light at the galactic center, a beacon powered by the awakened monster that had slumbered for so long. Chapter 25. Will Earth witness the cosmic merger? This brings us to a fascinating question. When the Milky Way and Andromeda collide, and their black holes merge in that spectacular finale billions of years from now, will Earth be around to see it? The honest answer is, probably not. At least not in anything like its current form. 4.5 billion years is an incredibly long time. The Earth is already about 4.5 billion years old, so we're talking about doubling the age of our planet. A lot can happen in that span. The first problem is the Sun. Our star is slowly getting hotter and more luminous over time. This is a natural part of how stars like the Sun evolve. In about 1 billion years, the Sun will be bright enough that Earth's surface temperature will rise dramatically. The oceans may start to evaporate, and our planet's climate will become increasingly hostile to life as we know it. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and evolve into a red giant, a bloated star, many times its current size. Depending on exactly how much the Sun expands, it might actually engulf Earth's orbit. Even if our planet isn't literally swallowed, the intense heat and radiation would render it completely lifeless, scorching the surface and likely stripping away the atmosphere entirely. So by the time the galaxies actually merge, the Sun will have long since stopped being a hospitable host star. Earth, if it still exists at all, will be a dead, scorched rock orbiting a fading white dwarf. But let's imagine for a moment that somehow, against all odds, Earth survived and life found a way to persist. Or perhaps humanity, or whatever succeeds us, has migrated to other star systems by then. What would such observers see? The collision itself would be a slow-motion spectacle unfolding over hundreds of millions of years. At first, Andromeda would grow in the night sky, changing from a faint smudge to a dramatic presence spanning tens of degrees. As the galaxies approached and began interacting, tidal forces would distort both of their structures. New stars would form in great waves as gas clouds were compressed. The night sky would become increasingly crowded and bright as the two stellar populations merged. During the close passages, gravitational interactions could fling stars, including potentially our solar system, into new orbits. We might find ourselves much closer to the combined galactic center than we are now, or we might be ejected to the outskirts or even into intergalactic space. The outcome would be essentially random from our perspective. If we ended up close to the action when the two black holes finally approached each other and began their final spiral, the view would be extraordinary. The central region would blaze with the light of matter falling into the feeding black holes. Jets might be visible, stretching across the sky. The gravitational waves from the final merger would be completely imperceptible to human senses, but instruments of that far future era might be able to detect them. The actual moment of black hole merger would be anticlimactic from a visual perspective. Black holes don't produce a visible flash when they combine. The gravitational waves would be the main signal, dying away as the combined black hole settled into its new configuration. But the aftermath would reshape the galaxy we call home. The newly merged black hole would continue feeding on disturbed gas for some time, potentially remaining active for millions of years. The new galaxy, sometimes called Milky Way in speculative discussions, would settle into a new equilibrium, probably an elliptical shape very different from either of its parent spirals. Whether any intelligent observers will be around to witness this cosmic drama remains to be seen. Life on Earth almost certainly won't make it that far under natural circumstances. But the universe is a big place, and 4 billion years is a long time for life to spread, evolve, or emerge elsewhere. Somewhere in the merged galaxy, there might be eyes looking up at the sky, witnessing the culmination of a process that began when the Milky Way and Andromeda first noticed each other's gravitational pull across the void. Chapter 26. The Fermi Bubbles, Echoes of an Ancient Awakening. We've talked a lot about how quiet Sagittarius' star is today, but there's dramatic evidence that it wasn't always so subdued. Enormous structures stretching above and below our galaxy that seem to be the remnants of a powerful outburst from the galactic center. These structures are called the Fermi Bubbles, named after the space telescope that first clearly revealed them. They're huge, extending about 25,000 light-years above and below the plane of the Milky Way. If you could see them with your naked eye, they would cover more than half the sky. The bubbles are filled with high-energy particles that emit gamma rays and X-rays. Their sharp edges suggest they're relatively young, probably no more than a few million years old. Something at the center of the galaxy released an enormous amount of energy, inflating these bubbles like giant cosmic balloons. What could have done this? There are 2 main candidates: a burst of star formation in the central region, or an outburst from Sagittarius' star itself. The star formation scenario suggests that millions of years ago, a wave of new stars formed near the galactic center. The most massive of these stars would have lived fast and died young, exploding as supernovae and driving powerful winds into the surrounding space. The cumulative effect of many such explosions could have inflated the bubbles. The black hole scenario is more dramatic. If Sagittarius' star went through an active phase, even briefly by cosmic standards, it could have released enough energy to create the bubbles. Active galactic nuclei in other galaxies routinely produce such outflows, driving jets and winds that carve out enormous cavities in the surrounding gas. Recent evidence seems to favor the black hole explanation, or at least a major contribution from it. The geometry of the bubbles is consistent with jets from the galactic center, and there are other hints that Sagittarius' star was more active in the recent past. Those light echoes we discussed earlier, which suggest the black hole was much brighter just a few hundred years ago. If the Fermi bubbles really are evidence of a past outburst from Sagittarius' star, they tell us something important. Our galactic black hole can wake up. It has woken up, and given enough fuel, it could do so again. The energy required to inflate the bubbles is staggering, equivalent to millions of supernovae. If Sagittarius' star was responsible, it must have been feeding at a rate far higher than it is today, probably approaching the levels seen in actively feeding black holes in other galaxies. What triggered that feeding frenzy? We don't know. Perhaps a large gas cloud fell toward the center. Perhaps a star was torn apart by tidal forces. Perhaps the remnants of a smaller galaxy merged with the Milky Way's core. Whatever happened, it was enough to transform our quiet black hole into a temporary monster. The bubbles are now expanding outward, gradually thinning and cooling as they age. Eventually, they'll dissipate into the general halo of our galaxy, their energy spread out too thinly to detect. In 100 million years or so, there may be no trace of them left. But for now, they stand as monuments to Sagittarius' star's capacity for violence, a reminder that the quiet giant at the center of our galaxy is not always so peaceful. Chapter 27. The Anthropic Principle and Black Holes. Here's a philosophical question to ponder. Is there something special about the fact That we live in a galaxy with a relatively quiet supermassive black hole? Could Sagittarius Star's dormancy be part of why we're here to study it? This line of thinking is related to what philosophers and physicists call the anthropic principle, the idea that any observation we make about the universe is necessarily conditioned by the fact that we exist to make it. We can only study universes or, in this case, galaxies that are compatible with observers like us existing. Consider what would happen if Sagittarius Star were much more active. A constantly blazing quasar at the center of our galaxy would bathe the Milky Way in intense radiation, X-rays, gamma rays, and high-energy particles. Planets close to the galactic center might have their atmospheres stripped away. Even at our comfortable distance of 26,000 light-years, the effects could potentially be harmful to life. Some researchers have suggested that the habitability of a galaxy might depend partly on the activity level of its central black hole. Galaxies with very active nuclei might be less hospitable to life, at least during the active phases. By this reasoning, the fact that we're here studying Sagittarius Star from a safe distance, while it quietly naps at the galactic center, might not be entirely coincidental. Of course, we shouldn't push this argument too far. Life is remarkably adaptable, and we don't really know how active Sagittarius Star was during the billions of years when life on Earth was evolving. Short outbursts, like the one that might have created the Fermi bubbles, happen on timescales of millions of years, brief by cosmic standards, but potentially significant for life. There's also the question of whether active black holes are always harmful. The jets and winds from an active nucleus stir up gas throughout a galaxy, potentially triggering star formation in some regions even as they suppress it in others. Some of the heavy elements needed for life might have been created in the violent environments around active black holes. It's possible that a certain amount of black hole activity is actually necessary for creating the conditions for life. What we can say is that right now, Sagittarius Star's quietness makes it an excellent subject for scientific study. We can probe its environment in detail without the overwhelming glare of an active accretion disk. We can track the orbits of nearby stars without their light being drowned out. We can image its shadow without interference from powerful jets. In a sense, we're fortunate to live in a galaxy where the central black hole is interesting enough to study, but calm enough to study safely. Whether that's a coincidence, a selection effect, or just the way things happen to be, it's worth appreciating. Chapter 28, Black Holes and the Information Paradox. No discussion of black holes would be complete without touching on one of the deepest mysteries in physics, the information paradox. The problem goes like this. Quantum mechanics tells us that information can never be truly destroyed. Every physical process is, in principle, reversible. If you knew the complete quantum state of a system, you could run the equations backward and figure out what it was doing at any earlier time. But black holes seem to violate this principle. When something falls past the event horizon, it's gone from the observable universe. The black hole might eventually evaporate through a process called Hawking radiation, predicted theoretically, though never observed. But this radiation appears to be thermal, random, and featureless, carrying no information about what fell in. So what happens to the information encoded in everything that crosses the event horizon? Is it truly lost? Is it somehow preserved in the Hawking radiation in a way we don't understand? Is it stored on the event horizon itself? These questions have kept theoretical physicists arguing for decades. Various solutions have been proposed, including the holographic principle, which suggests that all information about what's inside a black hole is encoded on its surface. The firewall hypothesis, which proposes that the event horizon is actually a violent, hot boundary rather than a smooth one, and various exotic ideas from string theory. For Sagittarius Star specifically, we're not going to observe Hawking radiation. The black hole is so massive that its temperature is essentially zero, far colder than the cosmic microwave background. So it's actually gaining mass from its surroundings faster than it could ever lose it, through evaporation. But the information paradox still applies in principle. Everything that has fallen into Sagittarius Star over the past billions of years, gas, dust, Stars, possibly even smaller black holes, has carried information with it. Where does that information go? This isn't just a philosophical puzzle. It touches on the fundamental nature of reality, what the universe is made of at its deepest level, how quantum mechanics and gravity fit together, and whether our current understanding of physics is missing something crucial. Some physicists believe that solving the information paradox will require a complete theory of quantum gravity, a framework that describes how spacetime itself behaves at the smallest scales and highest energies. Such a theory might reveal that black holes aren't quite what we think they are, or that the event horizon isn't as absolute a boundary as it appears. For now, the information paradox remains unsolved. Sagittarius, a star, keeps its secrets, swallowing everything that crosses its event horizon and giving us only the faintest hints of what happens inside. Perhaps one day we'll understand. Perhaps some mysteries are destined to remain forever out of reach. Chapter 29: The Future of Black Hole Science. As we near the end of our journey through the story of Sagittarius, a star, let's look ahead to what the coming decades might bring. We're living in a golden age of black hole research. The first images of black hole shadows have been captured. Gravitational waves from black hole mergers are being detected regularly. Our understanding of how black holes feed, grow, and influence their surroundings is advancing rapidly. For Sagittarius, a star specifically, several developments are on the horizon. Better images are coming. The global network that captured the first image is being expanded, and space-based editions would dramatically improve resolution. We might soon be able to watch the material around the black hole move in real time, creating movies instead of static snapshots. Spin measurements might finally become possible. Through a combination of X-ray polarimetry, gravitational wave observations, and more precise imaging, we may be able to determine how fast Sagittarius, a star, is rotating, a key piece of information that would tell us about its history. Gravitational wave astronomy will mature. Space-based detectors will extend our ability to detect gravitational waves from supermassive black holes. If something spirals into Sagittarius, a star, we might hear it. Multi-messenger observations will become routine, coordinating observations across different types of light, and gravitational waves will give us a more complete picture than any single method alone. Theoretical advances will continue. As we gather more data, our models of black hole physics will be refined and tested. Some theories will be confirmed, others will be ruled out, and new questions will emerge. New discoveries will surprise us. History shows that whenever we develop new ways of observing the universe, we find things we didn't expect. The black hole at the center of our galaxy has already revealed surprises, and there are surely more to come. Perhaps most exciting is that the techniques developed to study Sagittarius, a star, can be applied to supermassive black holes throughout the universe. Each one we study adds to our understanding of how these monsters form, grow, and shape their host galaxies. In a sense, Sagittarius, a star, is our local laboratory for black hole physics. It's close enough to study in detail, interesting enough to challenge our theories, and quiet enough to observe without interference. What we learn from it illuminates the entire population of supermassive black holes scattered throughout the cosmos. Chapter 30: A Monster in Our Midst. Let's step back and reflect on what we've learned about the object at the center of our galaxy. Sagittarius, a star, is a supermassive black hole containing about 4 million times the mass of our Sun. It's been there for most of the Milky Way's history, growing slowly by consuming gas, dust, and occasional stars. Its event horizon is about 12 million kilometers across, large enough to swallow several solar systems, yet tiny compared to the galaxy it anchors. Right now, it's remarkably quiet. The faint glow of radio waves and occasional flickers of X-rays are almost all we can detect. Compared to the blazing quasars powered by black holes in distant galaxies, ours barely registers. But it hasn't always been this way, and it won't be this way forever. Evidence suggests it was much more active in the recent past, and the eventual collision with the Andromeda galaxy will wake it up for a truly spectacular finale. Billions of years from now, The discovery of Sagittarius A star is a triumph of human curiosity and ingenuity. We can't travel there, we can't send probes. All we can do is catch the faint signals that reach us across 26,000 light-years of space. Yet from those signals, we've pieced together a remarkably detailed picture of one of the most extreme objects in the universe. We've tracked stars orbiting it, measuring their paths with incredible precision. We've detected its faint emissions across the electromagnetic spectrum. We've even captured an image of its shadow, the dark silhouette where light falls in and doesn't come out. Each observation has confirmed our theoretical predictions while raising new questions. General relativity holds up beautifully in this extreme environment. Black holes behave the way we expect them to, and yet there's so much we still don't understand. What happens inside the event horizon? What causes the occasional flares? How fast is it spinning? What will happen when it merges with Andromeda's black hole? These questions drive ongoing research and will inspire new generations of scientists to keep looking at the heart of our galaxy. There's something profound about knowing there's a monster at the center of our cosmic home. Every star in the Milky Way, including our Sun, is connected to that central darkness by gravity. The black hole doesn't directly influence life on Earth. We're far too distant for that. But it's part of the same system, the same gravitational web that holds our galaxy together. When you look up at the night sky and see the pale band of the Milky Way stretching overhead, remember that at its heart lies something extraordinary. An object so massive that nothing can escape its pull. A region of space so warped that time itself loses meaning. A cosmic mystery that humanity has worked for decades to understand. Sagittarius A star. The monster in our midst. The quiet giant waiting at the center of everything we call home. Chapter 31, The Cosmic Food Chain. Let's zoom out even further and think about where Sagittarius A star fits in the grand cosmic food chain, the hierarchy of gravitationally dominant objects that structure the universe. At the smallest scale are planets, like our own Earth. Planets are dominated by the gravity of their host stars. Earth doesn't move through space on its own terms. It follows the path dictated by the Sun's gravitational pull, completing one orbit every year without fail. Stars themselves are not independent either. Our Sun is just one of hundreds of billions of stars in the Milky Way, all orbiting the galactic center. It takes the Sun about 230 million years to complete one lap around the galaxy. In the 4.6 billion years since our solar system formed, we've made this journey roughly 20 times. And what's at the center of all these orbiting stars? Sagittarius A star. The supermassive black hole is the gravitational anchor of our entire galaxy. Every star, planet, moon, asteroid, and grain of dust in the Milky Way is ultimately connected to this central mass. We're all part of the same cosmic system, bound together by gravity. But the hierarchy doesn't stop there. The Milky Way itself is part of a larger structure called the local group, a collection of more than 80 galaxies gravitationally bound to each other. The two largest members are the Milky Way and Andromeda, each with their own supermassive black holes. The local group, in turn, is part of an even larger structure called the Virgo supercluster, which contains thousands of galaxies. And supercluster connect together into even vaster structures, long filaments and walls of galaxies, surrounding enormous voids where almost nothing exists. At every level of this hierarchy, gravity is the organizing force. And at the heart of most major galaxies sits a supermassive black hole, anchoring the whole system. This perspective helps us understand why supermassive black holes are so important for cosmology. They're not just interesting objects to study, they're structural elements of the universe. Understanding how they form, grow, and influence their surroundings is essential for understanding how the cosmos itself came to be the way it is. Sagittarius A star may seem like a distant, exotic object, but it's intimately connected to everything we know. The atoms in your body were forged in stars that have orbited the galactic center for billions of years. The planet you live on exists in a galaxy that Sagittarius A star helped shape. In a very real sense, we are part of the black hole's cosmic family. Chapter 32, Black Holes in Popular Culture. It's worth taking a moment to consider how black holes have captured the public imagination and what that means for science education. Black holes are everywhere in popular culture. They appear in movies, television shows, books, video games, and countless other media. They're often depicted as cosmic menaces, swirling vortexes of doom that threaten to swallow unwary spaceships and destroy civilizations. These depictions range from reasonably accurate to wildly fantastical. Some films have consulted with actual physicists to portray black holes realistically. Others throw scientific accuracy out the window in favor of dramatic spectacle. The public fascination with black holes is understandable. They represent some of the most extreme and counterintuitive aspects of physics. The idea that there are objects from which nothing can escape, where time and space behave in bizarre ways, where our understanding of the universe breaks down, that's inherently dramatic and compelling. But this fascination comes with responsibilities. When people encounter sensationalized or inaccurate portrayals of black holes in entertainment, they may come away with misconceptions. Black holes aren't cosmic vacuum cleaners that suck in everything around them. They don't randomly appear and start consuming star systems. They obey the same laws of physics as everything else. Sagittarius, a star, is a perfect example. Despite being incredibly massive, it poses no danger to Earth or our solar system. We're far too distant for its gravity to have any direct effect on us. The Sun's gravity completely dominates our local environment. Even if Sagittarius, a star, suddenly doubled in mass, we wouldn't notice any difference in our daily lives. One of the valuable things about communicating science to the public is helping people understand the difference between science fiction and science fact. Black holes are remarkable enough without exaggeration. The real science is often stranger and more fascinating than anything fiction writers could invent. The image of Sagittarius, a star's shadow, that was released to the world is a perfect example. That blurry orange ring might not look as dramatic as Hollywood's special effects, but it represents something far more profound, direct visual evidence of an object whose existence was predicted mathematically a century ago, captured by a planet-spanning network of telescopes working in concert. That's more impressive than any fictional portrayal. Science communication matters because it helps people understand their place in the universe. Knowing that there's a supermassive black hole at the center of our galaxy, understanding what it is and how we discovered it. These things connect us to something larger than our individual lives. They remind us that we're part of a vast, strange, magnificent cosmos. Chapter 33, The Philosophy of Cosmic Insignificance. Thinking about objects like Sagittarius, a star, inevitably leads to some philosophical reflection. When you contemplate something containing 4,000,000 times the mass of the Sun, hidden at the center of a galaxy containing hundreds of billions of stars, it's natural to feel small. This feeling of cosmic insignificance can be interpreted in different ways. Some people find it depressing, a reminder that individual human lives are brief flickers in a vast, indifferent universe. Our planet is a tiny speck orbiting an ordinary star, in an unremarkable corner of one galaxy among trillions. In the grand scheme of things, does anything we do really matter? Others find this perspective liberating. If the universe is so vast and our lives so brief, then the small worries and anxieties that consume us day to day seem less consequential. We're free to create our own meaning, to appreciate the sheer improbability and preciousness of conscious existence in a cosmos that is mostly empty space and dead matter. Still, others find wonder. The fact that we can understand the universe at all, that creatures evolved on a small planet, can work out the physics of black holes, predict their properties mathematically, and then detect them across thousands of light years, is remarkable. We are the universe becoming aware of itself, as some philosophers have put it. Sagittarius, a star, has been there for billions of years, long before humans existed, and it will be there for billions more after we're gone. It neither knows nor cares about our existence, and yet we know about it. We've mapped the orbits of stars around it. We've captured its image. We've puzzled over its mysteries and developed theories to explain its behavior. In that sense, the relationship between humanity and Sagittarius, a star, is profoundly asymmetric. The black hole affects us only through the distant gravitational pull, that helps maintain the structure of our galaxy. But we have reached out across the cosmic void and touched it with our understanding. There's something beautiful in that. For all our smallness, we have the capacity to comprehend things immensely larger than ourselves. We can hold the concept of a 4 million solar mass black hole in our minds. We can trace its history, predict its future, and place it in the context of cosmic evolution. Perhaps that's the most remarkable thing about the human condition. Not our physical size or our lifespan, but our ability to understand. A creature that lives for a century on a planet 8,000 miles across can contemplate objects that span millions of kilometers and exist for billions of years. That capacity for understanding is worth celebrating, even in the face of cosmic vastness. We are small, but we are not insignificant. We are brief, but we are not meaningless. We are the universe's way of knowing itself. Chapter 34, Unsolved Mysteries and Open Questions. Throughout this journey, we've touched on many things we don't know about Sagittarius, a star. Let me collect those mysteries in one place, because they represent the frontier of current research. First, there's the question of spin. How fast is Sagittarius, a star, rotating? Is it spinning at nearly the maximum rate allowed by physics, or is it relatively stationary? And which direction is the spin axis pointing? These basic properties remain poorly constrained despite decades of observation. Second, there's the detailed structure of the accretion flow. We know it's thin and sparse, but exactly how is the gas distributed? What are the temperature and density profiles at different distances from the event horizon? How do materials move as it spirals inward? Third, there's the origin and evolution of the magnetic fields. Where do they come from? How strong are they at different locations? How do they change over time? What role do they play in the occasional flares we observe? Fourth, there's the question of what triggers flares. Is it clumps of gas falling in? Magnetic reconnection events, stars passing close by, some combination? And can we predict them, or are they inherently random? Fifth, there's the history of the black hole's activity. How often has it been active in the past? What caused those active phases? How do they affect the surrounding galaxy? The Fermi bubbles suggest recent activity, but the full timeline remains unclear. Sixth, there's the population of objects orbiting close to the black hole. We've tracked many S-stars, but how many smaller objects, stellar mass black holes, neutron stars, white dwarfs might be lurking in the innermost region? These would be important for potential gravitational wave detection. Seventh, there's the ultimate nature of the object itself. Is Sagittarius, a star, definitely a black hole as general relativity describes, or could it be something more exotic? Every observation so far is consistent with standard black hole physics, but more stringent tests are always valuable. Eighth, there's the fate of information that falls in. The information paradox remains one of the deepest problems in physics, and Sagittarius, a star, is one of the best natural laboratories for studying it, at least indirectly. Ninth, there's the connection between the black hole and the galaxy's evolution. How exactly did Sagittarius, a star, influence the formation and structure of the Milky Way? What role did it play in regulating star formation? How will it shape the merged galaxy after the Andromeda collision? 10th, there's the broader context. How typical is Sagittarius, a star, compared to supermassive black holes in similar galaxies? What can it teach us about the general population of these objects? Each of these questions represents an active area of research. Scientists around the world are working on them, developing new observational techniques, building more powerful instruments, and refining theoretical models. Some of these mysteries may be solved in the coming decades. Others may persist for much longer. And the answers we find will inevitably raise new questions we haven't thought of yet. That's the nature of science. Every answer opens new doors. Every discovery reveals new mysteries. The universe has no bottom. There's always more to learn. Chapter 35, a personal reflection on cosmic wonder. As we approach the end of this journey, I want to share something personal. When I think about objects like Sagittarius, a star, I feel a profound sense of wonder that's difficult to put into words. Consider what we're talking about, a region of space where the laws of physics as we understand them break down. An object containing millions of solar masses compressed into a space. You couldn't cross at light speed in less than half a minute. A gravitational anchor that has held our galaxy together for billions of years while stars were born, lived and died around it. And we know about it. We've figured it out. Using nothing but the faint signals that reach us across 26,000 light years. Radio waves, infrared light, X-rays, we've reconstructed a detailed picture of something we can never visit, never touch, never experience directly. The tools we've developed for this investigation are themselves remarkable. Telescopes that cancel out atmospheric distortion in real time. Networks of radio dishes spanning entire continents, working together as a single instrument. Satellites peering at the universe from above the atmosphere. Mathematical frameworks that let us predict how space and time behave under conditions, utterly unlike anything in our everyday experience. None of this was inevitable. The universe didn't have to be comprehensible. The laws of physics didn't have to be discoverable by beings evolved on a small planet to find food and avoid predators. And yet here we are, decoding the secrets of cosmic giants. I think that's worth celebrating. In a universe full of darkness and indifference, consciousness emerged, life developed, intelligence evolved. And that intelligence turned its gaze outward, asking questions about the nature of existence and slowly, painstakingly finding answers. Sagittarius, a star, doesn't care about us. It has no mind, no awareness, no interest in what happens on Earth. But we care about it. We find it fascinating, mysterious, beautiful in its alien way. We've devoted lifetimes of work to understanding it. In that asymmetry lies something profound. The universe created creatures capable of wondering about the universe. Atoms arranged themselves into forms that could contemplate atoms. And one of those forms is you, listening to this story about a monster at the heart of our galaxy. That's not insignificance. That's something remarkable. Chapter 36. The story continues. Astronomy is not a finished science. It's an ongoing adventure, with new discoveries happening all the time. The story of Sagittarius, a star, that I've told you today is not the final chapter. It's just where we are in our understanding at this moment. Tomorrow, an observation might reveal something unexpected. Next year, a new instrument might come online that sees the black hole in a completely different way. In a decade, technologies we haven't invented yet might answer questions we don't know to ask. The researchers studying Sagittarius, a star, are pushing at the boundaries of the possible. They're developing techniques that have never been tried, coordinating observations across global networks, and analyzing data with cutting-edge computational methods. Each step forward is hard-won, and they're doing it for you, for me, for everyone who looks up at the night sky and wonders what's out there. Science is a communal enterprise. We learn together, we discover together, we expand the boundaries of human knowledge together. If this story has sparked your curiosity, if you want to know more, there are so many ways to continue the journey. Read books about black holes and cosmology. Watch documentaries about astronomical discoveries. Follow the news from space agencies and observatories. Consider supporting science education and research. Or just go outside on a clear night and look up. Find the constellation Sagittarius if you can. It's visible from most of the northern hemisphere during summer months. Know that beyond those stars, hidden by dust but revealed by human ingenuity, lies a monster waiting at the center of our galaxy. You're part of this story now. By learning about Sagittarius, a star, you've joined the chain of human understanding that stretches back through generations of astronomers, physicists, engineers, and curious minds. You've connected yourself to one of the most extraordinary objects in the universe. The story continues, and you're part of it. Chapter 37. The Art of Patience in Astronomy. One thing that often gets lost in popular accounts of astronomical discoveries is how long they take. We hear about breakthrough results, but we don't always appreciate the years or decades of patient work that made them possible. Consider the S-star observations. To track a star like Vesta through its 16-year orbit around Sagittarius, a star, astronomers had to make careful measurements for 16 years. Actually, longer than that, because you need multiple orbits to refine your understanding and reduce uncertainties. That means research careers dedicated to watching dots of light slowly move across the sky. It means applying for telescope time year after year, dealing with bad weather and equipment problems, refining techniques as technology improves, and waiting, always waiting, for enough data to accumulate. The astronomers who made the first measurements of S-stars in the 1990s had to trust that their successors would continue the work. The orbits they were measuring wouldn't be fully characterized until they retired or even died. Science operates on timescales longer than individual careers, longer than funding cycles, longer than attention spans. The image of Sagittarius, a star's shadow, is another example. The observations were made in 2017, but the image wasn't released until 2022. That's 5 years of data processing, algorithm development, checking and rechecking, and peer review. 5 years of painstaking work to transform petabytes of radio signals into a single blurry picture. And that picture itself was the culmination of decades of work, developing the theory of black holes, building the telescopes, inventing the techniques for very long baseline interferometry, coordinating a global network of observatories. The image was a single moment of triumph built on generations of effort. This is how science really works, not as dramatic breakthroughs by lone geniuses, but as the accumulated labor of countless people working together across years and decades. Slow, methodical, sometimes frustrating, but ultimately revealing truths that no single person could discover alone. When you hear about a scientific discovery, remember the patience behind it. Remember the graduate students analyzing data late at night. Remember the engineers maintaining instruments in remote locations. Remember the administrators writing grant proposals. Remember everyone who contributed a small piece to the vast puzzle. They deserve our appreciation. And when we think about Sagittarius, a star, this magnificent object at the center of our galaxy, we should remember that everything we know about it was won through human persistence, creativity, and collaboration over many lifetimes. Chapter 38, Your Place in the Cosmic Story. I want to end by bringing this story back to you, the person listening to these words. You exist in a universe containing 2 trillion galaxies. Each of those galaxies contains hundreds of billions of stars. Many of those stars have planets. The numbers are so large they stop having meaning. You can't really imagine 2 trillion of anything. In this unimaginably vast cosmos, you happen to live in one particular galaxy called the Milky Way. That galaxy has a supermassive black hole at its center, 4,000,000 times the mass of the Sun, lurking behind clouds of dust 26,000 light-years away. You didn't choose this. None of us chose the cosmic address we were born into. But here we are, inhabitants of a spiral galaxy with a sleeping giant at its heart. Every atom in your body was forged inside stars, stars that spent billions of years, orbiting around Sagittarius, a star, before exploding and scattering their contents into space. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was cooked up in stellar furnaces and spread through the galaxy to eventually form you. In that sense, you're not separate from the cosmic processes we've been discussing. You're a product of them. The same galaxy that contains Sagittarius, a star, also produced you. The same forces of gravity that hold the Milky Way together hold your feet to the Earth. The same laws of physics that govern the behavior of black holes govern the chemistry of your brain. You are star stuff. As a famous astronomer once said, you are the universe made manifest, conscious of itself, pondering its own nature. And part of that pondering has led you here, learning about a remarkable object at the center of everything you know. That connection between you, the stars, the galaxy, and the black hole at its center is not metaphorical, it's literal. We are all part of the same cosmic system, bound by the same forces, made of the same fundamental stuff. So when you look up at the night sky, know that you're looking at your family. The stars are your relatives, born from the same galactic material that made you. The Milky Way is your home in the deepest possible sense. and Sagittarius a star, for all its strangeness and power, is part of your story. Take a moment to appreciate that. In all the vastness of space, you're here. You exist. You can wonder about the universe and learn about its contents. That's a rare and precious thing. The monster at the center of our galaxy has been there for billions of years. It will be there for billions more. But you're here now, in this fleeting moment, aware of it. Make the most of that awareness. Let it expand your sense of what's possible. Let it remind you that reality is stranger and more magnificent than ordinary experience suggests. You matter. Not because the universe cares, it doesn't, as far as we can tell, but because you have the capacity to care about the universe. That capacity is worth something. It's worth a lot. Thank you for coming on this journey with me. The universe is full of wonders, and Sagittarius a star is just one of them. Keep exploring. Keep wondering. Keep looking up. And that brings us to the end of our journey, my friends. We've traveled from the first accidental detection of radio waves nearly a century ago to the first images of a black hole's shadow in our own cosmic backyard. We've explored the science, the history, the technology, the philosophy, and the big questions that still remain unanswered about the monster at the heart of our galaxy. Sagittarius a star is more than just an astronomical object. It's a window into some of the deepest mysteries of physics. It's a testament to human curiosity and ingenuity. It's a reminder of our place in a vast and ancient universe, and it's a promise of discoveries yet to come. I hope this voyage through the heart of our galaxy has given you a sense of wonder about the universe we inhabit. The cosmos is stranger, more beautiful, and more magnificent than most people realize. And Sagittarius a star is just one example of the extraordinary objects waiting to be discovered and understood. The scientists who study black holes aren't just satisfying their own curiosity. They're expanding the boundaries of human knowledge for all of us. Every new observation, every refined theory, every technological breakthrough adds to our collective understanding of reality. We all benefit from their work, whether we realize it or not. If you enjoyed this exploration, please consider leaving a like on this video. That simple action helps the algorithm show this content to more people who might appreciate a cosmic adventure. And if you haven't already, subscribe to the channel so you don't miss future journeys through the wonders of space and science. Ring that notification bell to be alerted when new videos drop. Share this video with friends, family, or anyone who might enjoy having their mind expanded by the mysteries of the universe. Science is always better when we explore it together. The more people who understand and appreciate the cosmos, the better off we all are. And please, drop a comment below telling me what topic you'd like me to explore next. Black holes, exoplanets, the Big Bang, dark matter, quantum mechanics, the search for extraterrestrial life. There are so many fascinating subjects waiting to be discussed, and I want to hear what sparks your curiosity. Remember, you are made of star stuff. You live in a galaxy with a supermassive black hole at its center. You are part of a cosmic story that stretches back billions of years and will continue for billions more. That's not just poetic language, it's literal truth. So keep looking up. Keep asking questions. Keep wondering about the universe and your place in it. That sense of wonder is one of the most precious things about being human. Thank you for spending this time with me. Until next time, stay curious, stay inspired, and never stop exploring. The monster at the center of our galaxy is waiting. But now you know its secrets. See you in the next adventure.